He did his PhD from Brandenburgische Technische Universität, Cottbus, Germany in 2008, and he did his MTech from IIT Kharagpur in 2004 and MSc from Jadavpur University in 2002. He was scientific assistant at Cottbus, BTU Cottbus, Germany from 2005 to 2008. He was a postdoctoral researcher at Kyung-hee University, South Korea from 2009 to 2017. And he was an assistant professor, Department of Physics, Jadavpur University from 2008 to 2017. And now he is an associate professor, scientist C at East Mohali, 2018 to present.
Yeah, thank you, Professor Senel, and thank you, the organizing committee, the advisory committee, and particularly Professor Borsar for giving me the opportunity to share some of our work to all of you. And with this, I want to start my lecture. And so let me share the screen first.
Sure. Sure, you start to share.
Yeah, so is it visible?
Yes.
Yes, yes.
Yeah. Okay. Okay, sir. So I'm starting my lecture. So let me tell you one thing very clearly, because I know what is the motivation of this kind of talk and so on, because I was the audience earlier, and I have attended very organized course organized by Professor Ward, and so I know the what kind of audience and what is the main purpose and so on. So I have designed my slide in such a way so that some of you can will be benefited if you are interested to, if you want to start with similar kind of work, and it can help you to survive within the low cost kind of research in better way, particularly which is perfectly suitable for Indian researchers. So that is my main motto. Whenever I give the opportunity to talk like this, I always start with these words, because I know how difficulties that we are facing every day in order to carry out our research, and that is also due to, it's kind of our hobby, our motivation to teach the students and do some good research so that our country can progress. So this is the only motivation part, and we are really very much committed, and then there is a balance, funding and resources and so on. So how can we make can make a real balance, and so that we can survive in little bit better way? So that is my main motivation to, for this kind of talk. I hope you will enjoy. So not much, high rigorous physics, and not much chemistry, because I know the audience also, what kind of audience are there. So whenever you feel any uncomfortable or any curiosity, anything, so you can stop me anytime, or we can discuss at the end. So it's up to you. So yeah, this is you can see our overview of the building. It is a really basically new institute of DST, which is dedicated for nanoscience and technology. So nanoscience is, so everyone is doing in different lab and different institute, but this is the institute under DST, Government of India, which dedicatedly for nanoscience and nanotechnology. So this is one of the youngest institute of DST, you can say. So now this is the time that we are moving towards new campus. So this is really, so far we stayed in the Tanjit campus, and now we are moving. So that's why we are little bit busy to shifting the things, and it's really big work, from shifting the instrument from one place to another place. And so that's what we are basically the phase of transporting the, equipments. So let me introduce this thing, because this is very important. Whenever we stay the place, we have to love the place, otherwise we cannot perform our best work, or let's say we'll be not happy, right? So I think uh, I, so pointer, Okay, so you see, this is basically Chandigarh and Mohali is very adjacent. It's like 5 minutes traveling. So you can sometimes we say Chandigarh, sometime, but is the place is basically Mohali. Okay, and which is under Punjab. So at a glance, you can see it's very nice traffic. This is like post-independence. Professor, I mean Pandit Jawaharlal Nehru, he made with the French architect, and it's really very nice without even electronic traffic. Traffic signal, one can reach one place to another without doing any accident and so on. So this kind of roundabout now in Salt Lake, and many places you can see. But this is immediately after post-independence plan, and this I really like. And some of the other architecture like these like water harvesting plan and that time after post independence, because that Pandit Jawaharlal Nehru he made with the French architect, and he really made very nice planning with this and some of the place like you can see this is all waste materials. They use waste materials to make a rock garden. So this is a like huge area. They make many creative feature with the waste materials. So they really recycle the things in very nice way. So this is the another place that attracts me. This is another artificial lake that you can stay at the evening time, and very big actually. I do exactly I don't know the dimension, but very big place, and many tourists come. Usually they are boating and so on. Some very nice big zoo is there, very close by. And this is again post independence architecture. This is called capital complex. So the Chandigarh is the capital of three states like Punjab, Haryana. Yeah, two states mainly. So Punjab and Haryana. So that's why these two signify like one Punjab, one Haryana, something like that they said. And yeah, that's all about the place that you are invited to visit. Those are still did not visited this place. With this I want to start the story. So the energy sources, right? So we all know how can we classify the energy sources. One is the renewable energy, another is non-renewable energy. That means like after 20 to 30 years or so, we will face the real problem if we don't generate renewable energy sources, because the fossil fuel based economy is going to finish after a certain period of time, right? So this is the limited resources. We are lucky enough that we are surviving, but our next generation they have to really heavily depends on the renewable based energy sources. So out of them, like solar energy is one of the big resources that people are considering. Another, of course, we are using hydrothermal and wind energy, geothermal, biomass as well. So these are the few renewable energy that we are basically focusing on. And this is the process that we all know, the energy transformation process, right? So energy conservation law we know, but we can convert the energy from one form to another form, right? Like these are the cartoon basically. So the chemical energy to mechanical energy, and many others like light to chemicals, chemical to mechanical. So this is today I'm going to talk something about the energy transformation process. So, and these are different form of energy we know already. So mainly this talk I divided into two parts. One is the mainly focus on the piezoelectricity, another is the triboelectricity, because these two parts I will focus. So let me introduce you what is piezoelectricity, since also although many of we know, because this is very old phenomenon, and in textbook physics it is there. So it is again the energy conversion process, mechanical energy to electrical energy. You can see we are hammering it, and we are generating basically electrical current, right? You see the ammeter is basically moving. That means the current is flowing through the circuit. This is the cartoon again. If you hammer it, you can again lighten the bulb. So this is mechanical energy to electrical energy conversion process. So another example, classic example is every day we use, in the kitchen is the gas lighter. So we are basically familiar with this lighter, where it is basically consist of a piezoelectric crystal here. So once we hammer by the thumb, and then there is a gap between the two electrodes, and there is air. So that air is get ionized, and it's come out as a spark. And whenever it comes in front of the LPG, we get the fire. So that's the basic principle. But the main things attracts here to me is the small press not too much press, right? Whenever we press our gas lighter, that give rise, some kilovolt kind of order of amplitude of voltage that give rise the ionize the air, so very much big voltage basically. So small squeeze or press is giving rise very high voltage or let's say current so forth. So and this is the history we should discuss a little bit, because piezoelectric effect was first discovered by the Curie brothers. We all know, 1880. So this, if we look this particular, year of invention, you can correlate with the some World War time, because the due to the necessity, some discovery, sometime, it happened actually. So piezoelectric was that kind of discovery that really, at that time, it was necessity to signal, I mean, transfer from one side of ocean to another side. So it's a transducer type of device was a necessity that time. So they discovered the piezoelectricity, and in order to sonar, hydrophone, and so on. There are history basically, but this year of invention is very important to understand the fact. So and then later on, this Professor Liebman, he discovered 1881. You see, the next year, fundamental thermodynamic principle he established, and based on that, he said that the converse effect. That means direct effect is if you pressure it, you have the electrical output, right? So in reverse way, if you put the electrical output, then you should get the pressure, right? That means the vibration. So if you give a AC kind of let's say electric field, then you will get the vibration. So it's like a motor, right? So reverse effect, converse effect, basically more one can design the motor based on the converse effect. And the direct effect means you are giving the pressure or force and you are getting the electrical output. So it is, we call the energy harvester. So you can generate the energy, right? So these two, direct and converse effect, both are applicable for several applications. Yeah, so that's what we discussed, direct effect and converse piezoelectric effect. And you can see once why this voltage generation is happening. This again I will discuss in the next slide. You see, this is a simple molecular model, how piezoelectricity work basically. Let me discuss in very simple manner. So the main necessity thing is, I mean, one should have the non-centrosymmetric kind of crystal. So symmetry breaking phenomena is important. In many cases in physics, we know, even particle physics also, if we break the symmetry, then many things happens. Here, if you have the crystal, and that if that has the non-centrosymmetric kind of symmetry, the space group, then you can imagine, okay, you have the piezoelectricity kind of phenomena. So how it works, let's say, so this is basically center of and positive and negative charges of each molecule that coincides. So as a result, it is act as an like neutral molecule. Okay, so once we give a pressure, then what happened? The internal deformation takes place. As a result, this small dipole basically formed. You see, this side is became negative, and this side became a positive. So it acts as a dipole, and that is the responsible source for the polarity. Once we apply the pressure. So one real example is the quartz in a watch, wristwatch, right? We all have the wristwatch, and that consists of a quartz crystal. This is another wide application of the piezoelectricity, like gas lighter, and this is another example apart from the hydrophone and many other sectors. So quartz crystal is basically in the watch, it is calibrated with the signal, with the transducers, and then we get the time. So how that quartz work? You see, when the no stress is there, then this act as an like neutral mode. And once we apply the tension, for example, if we give a pressure like this, if we this way, and you can see this is Si and this is O. So this became positive and this became negative. You see, this is negative. See, in other way, if we compress it, if we compress it, you can see this is a negative polarity and this is positive polarity. So is acting as an like dipoles. So based on the piezoelectricity, there are several applications. So you can see this tree, where these are the the expected technology that forthcoming technology that can will get in near future. One of the application is like Internet of Things, piezo and triboelectric nanogenerator, hybrid energy-based device like MEMS, and many others, basically. So these are the is kind of dream tree that people want to fulfill by the piezo and triboelectricity and pyroelectricity kind of phenomenon. So as we discussed, like next 20 to 30 years, we should have, I mean, we may have, the deficiency of the renewable and non-renewable energy resources. So similarly, next 30 years, like we'll be also heavily depending on the sensors, so that will be like embedded everywhere, home to health sectors, mobile device, industry, building. And now this is one of the example during this pandemic situation, how we are interacting each other. So we have a internet of things that can connect each other. And so in next 30 years, like we will be even we will heavily depend on the different kind of sensor, and that eventually needs the power source, right? Otherwise, how they will work. So, and then the main challenge is how you will replace it. After a certain period of time, you have to change the battery and so on. So that's really challenge, like trillion of sensor. How can you do? How will do the power management? This is a really big concern. So that's why many topics into coming into the picture, and it became even more severe when we think in the healthcare sector. For example, like the this is the pacemaker you can see, and that really need a battery power source, right, in order to function it. So, and after 5 to 7 years, even though if you choose very good pacemaker, then again one has to replace the battery. Pacemaker replacement may be not necessary, but one has to change the battery, and that is really painful because it happened in the older people. And surgery cost is a much higher than the cost of the battery. And think about the challenge, particularly those are like older people, or some very young people, whatever it may be the age. But it is really difficult, right? Now every time you have to replace. But we often see doctor advise us, okay, you pay a little bit more money so that you no need to change. It is lifetime warranty, sometimes we say. But in the case, it is not lifetime warranty at all. Doctors are very clever. They asked us, okay, you come frequently, we will check you. That means they check everything, whether it is functioning properly or not. And think about the toxicity, because battery consists of very toxic elements. So if it's get leaked, then we will be finished actually. So that's the real challenges that we are facing nowadays. But doctors, why they are clever? Because they know the age of when the people are going to the doctors, the age of like 70 or 60, and then they add another 7 years, then they think, okay, it's lifetime, yeah. Something like that they did, maybe. Or they are clever, like after 4 years they will definitely say, please, after 2 years you should change, it is better for you. Then that time our mentality change, and we said, yes, please do it. So initially they said lifetime warranty for sure. So the idea is, how can we make it sustainable pacemaker or other device also? So the concept of self-power devices coming into the picture. What is the self-power devices? For example, you see the self-charging unit. So it is like this woman riding the bicycle and producing a lot of vibration. And that vibration, if we can and collect the energy from the vibration, and if we feedback to power up the devices, then it is like self power devices. So it no need any power source, so called, actually. So that's the self power electronic. The concept of self power electronics is coming into the picture. So this is few demonstration so far in the publication, published report so far. So you see, this consists of, basically, once you riding the bicycle, that means the frequency is not homogeneous. That means you have a sometime different frequency, and amplitude is also not same always, right? So it is like AC kind of signal. So we have to make it DC. So this is kind of arrangement. This is we call a bridge circuit, right? So if we put a bridge circuit, then we can make it DC. So in a single, I mean, in a simple way, we can think like we have to make from AC signal to DC signal in order to charge the capacitor, so that you can make your device, self power. So we fit a capacitor in the device itself, and then whenever we ride the we give a vibration, then we can make it self power. Recently I bought a, the weight machine, bathroom weight machine. We can measure our weight every day. So, and that doesn't consist, any batteries. So battery free machine. I'm not advertising, but since I'm working in this area, so I get attracted and I buy sometime. Sometime also I found not good, not established technology, but this kind of one of my hobby, and this I found really good, because if you just 5 minutes, if you give a pressure like pump, not 5 minutes, even 1 minute, then you can completely, you can able to measure your weight. So you no need to think the change of the battery. Most of the cases, those you have this kind of equipment, I'm sure it is not working due to the replacement of the batteries. So let's say, for example, even measuring, BP and etc., all device, most of the case, because we are not, regularly, we don't like it actually to change the battery, and it consists of a lot of cost. And then management after, using it, and then we have to throw it, we have to recycle in proper way, so that it will, other people will not get affected, because it consists of very, very toxic element. If we throw to the environment, it harms us directly, I mean indirectly, and it harms the environment, so it's very dangerous. So that needs another management. So this kind of self power device is really attractive in near future. So many researchers are getting attracted to work in this particular area. And this is the demonstration. You can see by riding the bicycle, they can power up, calculator, different hygrophone, speedometer, and humidifier, and many others. So this is a kind of real demonstration that they shows it is possible to make it self power. This is a simple video that let me check. Yeah, yeah. So you see, this is basically this is piezoelectric device. Okay, and there is a two lead, because there is a electrode top and bottom, and it is connected with a DSO. This is digital oscilloscope. So you see, this hammering can give rise output voltage. So this output voltage, if we make a simple circuit, so that it will, if we can feedback it to this toy, so that it can move, then we can make it like self power. No need to, put the battery. So that's the kind of demonstration to make the self.
What happened? Technical problem? Going to
Any
on?
problem? Link problem?
No, we cannot see your presentation now. We can see you. Yeah, you can continue. What happened?
Okay, again you can share, no problem. Or if there is any problem, you can leave and then join again, so that.
Hello.
Hello, hello.
Yeah. Is it working, sir?
No, still no share.
Okay.
We
Okay.
are,
How
we
can
are
see?
observing your face, but no sharing is there.
Okay. Okay. Let me do it again. Share, done. Yeah. So is it okay
Yes,
now?
now it is okay.
Okay. Fine.
Now it is okay.
So yeah. So the main advantage, one of the advantage is like it is on at day and night. So this is very, very big, advantage in the case of vibrational based energy resources, because at the and in vivo and in vitro, like nowadays, implantable biomedical device is getting also attracted. So in that case, like, it should work under the dark as well, right? So the vibration, we say, like it is always on, like whatever day, night, extreme condition, even better, sometime. So it is really some sense it is advantageous, then we make little bit of some calculation where the intense energy sunlight which is required for photovoltaic cell is like this 20 milliwatt per centimeter cube. Whereas but it has some limitation, of course, like in medical implantable device, indoor operation, and so on. However, if we in the think of the vibrational based energy for the typical random vibration frequency like a hertz to kilohertz region, the available energy density is like 0.01 to 10 milliwatt per centimeter cube. So if we compare with this, so this is not a small energy basically. So this is a huge energy that we want to use for some useful manner. And there are many cases like where the small or low power electronics are there, where the convenience is one of the major factor. Like gigawatt or megawatt based energy, it is not like always necessary for many cases. So small power electronics is another research area where if you have a many, then you have to think, you have a more, you have to think how to step it down, right? So in that case, this kind of energy, particularly where low power is required, is very, very convenient and useful actually. So we should not compare directly with the photovoltaic cell, because photovoltaic cell is really useful for powering the houses and then industry and many others. But this kind of source like piezoelectric based or triboelectric based, mainly so far we are restricted to the low power based electronics, sensors and actuators. In the case of triboelectrics, recently they have given a Professor Jedel Wang, who is the pioneer I will discuss. He said some another new type of energy known as blue energy sources. So that is his dream, that he is thinking like he can compete with the photovoltaic cell. But that part I am not discussing because it's something different. Then another scope is there. Suppose if you look this table, there are many resources where we can collect our vibrational source, like industry, like environment, like wind, then temperature, then the ocean wave, many vibration from the vehicles, from the transportation. Thinking, if we think particularly this particular area, this attracts me always, because these are with us. Breathing, it is with us. Blood pressure, it is with us. Body heat, it is with us. Walking also, it is with us. We really every day everybody are walking like 300 steps at least. So jogging, swimming, these are like human body, so it is with us. So whenever we need the energy, we can talk a little bit more, let's say, then we can harvest it. Like now I'm talking more, so I can harvest, I can charge up my battery if we have the technology, right? So it is with us. If we can sing the song even to make the power our phone. So these resources is really very, very interesting to us, and I'm very much focusing on this particular area where we can harvest the energy from ourselves actually. Then there is another way how we can make it hybridize. What does it mean? That means like if we make like solar energy and this kind of piezoelectric or mechanical based energy sources together, so that's the idea given by Professor Jedel Wang's group. We can see this SC unit and NG unit. NG unit means nano generator. I will discuss what is nano generator, but shortly you can also imagine this is the mechanical energy based unit, and this is like the photovoltaic unit, like that works under the solar cell. Okay, so these they make it hybridized, so they make the different structure in such a way, some of the structure which is applicable for the photovoltaic cell, which is also applicable for the piezoelectric energy sources. For example, zinc oxide nanorod, it is basically piezoelectric materials, as well as it has the direct application in the case of solar cell fabrication. Okay, and then another hybridization way is to make chemical and mechanical energy together. How it is possible? Like you see, this is a piezoelectric based layer. So this is the membrane, and if we think about the lithium ion batteries, it consists of cathode and anode, and in between there is a membrane. Okay, so this is the basic component of a battery, and there is an electrolyte that should pass through from cathode to anode via electrolyte. So these electrolyte, they choose the piezoelectric materials. So this is the piezoelectric materials, this particular layer, and then they hybridize with the electrochemical battery cell. So and then they fit it with a shoe sole. So if if they step it, like if they walk somebody, and then it is possible to charge up the coin cell. So it is in future, like one can make very nice compartment in the shoe. We can place our coin cell, and if we go to office or shopping or any other places, we can charge it up. No need to put plug-in based technology that we are depending on currently, right? So that's the another approach people are thinking of. This waste heat to electricity, this we will discuss in the second lecture in the pyroelectricity. So these are the basically few example where few demonstration in different places like France and Israel, where they even crazy. They shows that, like 200 homes is possible to power up. So I always focus on the low power based energy, but it is like somebody we got from the Google, of course, some news where they have shown like 200 homes power up through the physioelectric means. So this is huge to me, but I'm not validated this thing, but I think it is possible if this kind of energy sources are available. If they place this underneath the road, because there are a lot of vibration is there. There are low cost materials we can place underneath the road. So it is possible to power up like 200 homes, and that's really crazy because it's really high power based energy. Apart from the low power based electronics, low power electronics. So this terminology is very new and becoming more famous is a nano piezotronics, because yeah, as far as we know piezotronics, mechatronics, right? So this is the another new terminology that we know, which is basically nano piezotronics. So if we look this terminology, it is consist of nanotechnology, nanomaterial based, piezoelectric is there. So this is the mixture of these two, and this is basically discovered by Professor J.L. Wang from Georgia Institute of Technology, USA. So he's the pioneer basically in this particular area, where he shows this I have shown you in the first slide in the beginning of this talk, where the small thumb produce the spark, right? So why it is happening, as I discussed, like there is a non-centrosymmetry breaking is happening, and there is a displacement of the ions, and we have a polarization, and this is electrical output basically. And that was 8080 it was discovered piezoelectricity, right? And then what he did in the 2006, that he got a little bit more attracted, because he shows the zinc oxide nanorods like this. You see, this is zinc oxide nanorods, and this is AFMT. So he passed the AFM through the zinc oxide nanorod. His intention was to measure or to estimate the Young modulus of each nanorods. So that was his motivation of this work. And then he found, once it's passing through the this AFM tip to the this zinc oxide nanorod in different places, from here to and then a little bit up, then it's going to the top, and then it's going to the down again. And then he found whenever it's crossing it, and there is a voltage generation, there is a spike. You see, a lot of spike if we consider the total area. Then he discussed, okay, this is something different phenomenon, and then he found that zinc oxide nanorod is a semiconducting material, but it has the piezoelectric property. So he's the person who has given the name of nano generator. Generator we know, right? So it generates basically energy. However, this terminology nano generator, it was created by Professor J.L. Wang in 2006. So this is the first paper where he reported this work, and it was published in Science in 2006. So this is very nice article. Anybody can read it, if they read, and they can able to understand. It is written in such a common way. That's the way to present in the Science magazine, right? So one can read it if somebody are interested. If somebody want it, and then I can also send the paper, because I have it. Yeah, I have it in this paper also, of course. So yeah, with this, and then recently in 2015, like people, yeah, choice as a winner of Nobel Prize, like this is kind of, yeah, tag he got. People nominated him at 2015, but yeah. Uh, so nano generator we know, right? based on the zinc oxide nanorod. So what is the basic unit? You can see this is zinc oxide nanorod, and then one should have the two electrodes. This is the simple structure. So one should make the nanorods with zinc oxide, and then one has to deposit the electrode with aluminum foil or gold coating or silver coating or any other conducting means. So in practice, it is look like this. Then one has to connect these two lead with the some capacitor or some bridge circuit in order to harvest the energy. So that's the basic unit. Another is like one can make it, single nanowire, and then if we, if we make it back and forth, and then if we can amplify it, then we can also able to track the what kind of, the noise or signal, mechanical signal we are, it is available around us. So that is the another application of this kind of device. So it is not only harvest the energy, it can sense the mechanical agitation. So it has the sensoric application as well, right? So one is the energy generator, another is a mechanical, I mean the pressure sensor or force sensor. This kind of application is there. So now what are the limitations? So you can see it has many advantages like biomedical sensor. It can flow, it can be power up through the blood flow or muscle contraction, so the we can harvest our own energy. It can also possible to tiny gas sensor that can run or wind through the acoustics wave. Pathogen monitor, it can be possible to power up by water flow, because water flow also generates the mechanical energy, and then portable electronics that can be hooked up with the nanowire in shoe. That means again our mechanical movement can again, it can power up several mechanical, I mean several portable electronic gadgets. Yeah. So that's the main advantage with the nano generator, because the device is smaller. In many cases, the since the device is smaller, so the requirements of power is also getting smaller. That is very attractive. So you no need always megawatt or gigawatt. So we are going towards the low power energy. You can see nowadays if we put in our laptop on, then if we go away, it will reduce the power. It has a own mechanism to make it, to go to the some other mode, so that it can save the energy. So we are moving towards the the low power energy based sensor and device in near future. But the main concern with the piezoelectric device is the one is main bottleneck is the toxicity, and it is brittleness, because most of the materials like zinc oxide and PZT is the most, is a mainly typical piezoelectric materials, lead zirconium titanate, barium titanate. These kind of materials basically made mainly you can classify as ceramics based materials, and this it is they are brittle in nature. So if we give a the mechanical agitation, that sometime after certain period of time it is not work, or it doesn't work, because it get it break it, basically it get break. So the mechanical motion is not I mean, yeah. So it needs a flexibility. So that's why polymer-based materials into coming into the picture. Another thing is like lead, since it consists of the lead, the PZT, and it is toxic in nature. So this is another disadvantage with the ceramic-based material. But the advantage with the ceramic-based materials is the piezoelectric coefficient is very high. So if you give a very small pressure, you will get a very high voltage output. That's what we are getting in the gas lighter, basically kitchen lighter. So very small spark, but we are getting very high voltage throughput. So that is the main advantage with ceramic based materials. But where mechanical motion is extreme, like you can't able to control, then it is difficult, because it will break after certain period of time, and then it will not work. So we need to make either composite based materials mixed with the polymer, or we have to depending on the polymer based materials. So that's the main idea, to switch to the polymer-based electronics. So you can see there are many, yeah, if I quantify like blood flow, walking, finger typing, it has a sufficient input energy, which is good enough to power up the tiny piezoelectric based device. So if we categorize this, what kind of piezoelectric materials what are the materials those exhibits piezoelectric properties? then we have to make this kind of table where you can see one is belonging to the natural sources, another is the synthetic. Synthetic, what does it mean? That means we have to synthesize them, we have to fabricate them, right? And another is the natural, that is available with us basically, like silk, DNA, quartz, topaz, so these are the all natural resources. Even chitin, it is existing in the and this kind of resources like prawn shell, crab, etc. This is human bone. Again, it exhibits the piezoelectric property in nature. Some bacteria also shows piezoelectric properties. Silk, collagen fiber, I will discuss in little bit greater detail on this. It also exhibits piezoelectricity. DNA, it also have the piezoelectricity. So these are the natural resources. Even sugar. So synthetic materials, as I discussed, as I mentioned, PZD is the most famous, but its main disadvantage with the lead. And in European Union, it is like, they don't allow it to use anymore. So that's why people are working on lead-free based piezoelectric. So this is the another research area known as lead-free piezoelectric based, lead-free based piezoelectric materials. So zinc oxide, and then potassium niobate, these are the materials basically where you can make it lead free. Even PVDF, that is another interesting materials. So as I mentioned, it is toxic, harmful, and it is harmful for the society. It is brittle. So long-term power supply is a problem. Whereas the polymer-based materials, nano generator or piezoelectric-based device, it is flexible and shape adaptive. What does it mean? That means you can make it any shape, like you can make it matte, right? So if we like 10 feet by 10 feet our room, if we make it a floor with the polymer, and that's what in many laboratory we have. So if we make with the piezoelectric based polymer, which is not costly as well, so you can if you walk around, then again you can power up your stuffs. I mean the electronics, right? You can make it nice circuitry to plug in to power up, or let's say charge our capacitor and so on. So this is the one major advantage, and that's the reason I have survived in my earlier places, Jadavpur University, in very optimum way. I have I mean competed in with many research group because of the polymer. So it has their own advantage, and no need any sophisticated based research resources like high vacuum technology, deposition unit. No need. You have to buy the polymer, and there is a magnetic stirrer. You have to make the solution, and then you can fabricate your nice device. So this very easy way to survive. And it is very low cost, basically easy processing, as I mentioned. So these are the very it's really attractive points. So let us discuss this is model polymer. That's why I'm discussing these materials. Please don't get bored. So this is known as PVDA, polyvinyl fluoride. Okay. So this consists of a monomer like this, and it has a repeated unit of this. So you see, this is the backbone, carbon-carbon. It consists of CH2 and CF2. So very simple polymer, basically simple molecule, simple monomer. So not complicated like is a hyper branch or blah blah blah. So very simple CH2 and CF2. So if you look this particular structure, this is cross-sectional view. If you look from this side, you can see two carbon atom like red, and these are the hydrogen. This is fluorine. Hydrogen is relatively van der Waals radius is smaller than the carbon, and then the hydrogen, right? So hydrogen is the smallest one here. So since H is the plus and F is the minus, so it acts as in like dipole. So this is the basically main resources that's the reason to get the piezoelectricity. So why this is so important? Because it not only the piezoelectricity, once you have the device, like then you have a three different phenomena in your hand. One is the piezoelectricity, because if we apply the mechanical stimuli, you will get the piezoelectricity. So it has the two main application like pressure sensor and energy harvester, mechanical based energy harvester. Then I will discuss about the pyroelectricity. So what is pyroelectricity? if we change the temperature, like here we change the pressure, right? Different pressure amplitude. Similarly, if we change the temperature, so if we give the temperature pulse, then again we can produce the current and voltage, which is known as the pyroelectricity. So it has an application like thermal energy harvester as well as the infrared sensor, heat sensor. So you see the single materials, it can exhibit piezoelectricity, it can also exhibit pyroelectricity, it also exhibits ferroelectricity. So what does it mean, ferroelectricity? So if you give the electrical stimuli, like if we apply the electric field, then if you reverse it back to zero, then you can see some remanent polarization. So ferroelectric loop, so is if you reach to the zero electric field, then again you have a remanent polarization, which is known as the memory. So there are USB drive, flash memory drive, many application is there. Those are based on the ferroelectricity. So these two coefficient is very important. If we check this is D, this is piezoelectric coefficient. This is nothing but a thermodynamic relation. So if we apply the stress, D sigma, sigma is the stress, mechanical energy, right? So we are changing the polarization when electric field and temperature is the constant. Electric field and temperature, pyroelectricity is the constant. Very simple, right? So piezoelectricity means if I applying the stress, we are getting basically change of polarization when electric field and temperature is constant. Similarly, the pyroelectricity, if we change the temperature, then we are creating the change of polarization when electric field and stress is constant. These two coefficients are very important in order to describe the piezoelectricity and pyroelectricity. So yeah, so let me discuss this one because this is very important. So once you buy the Pvda, very cost-effective polymer, this is because it has a use in the paint industry. It is epoxy resin. So you can buy, if you expend like 10,000, you can buy 5 kilograms. Very cost-effective, and it is semi-crystalline in nature. What is semi-crystalline means? That means it has crystalline lamella and amorphous resin. So it is not like inorganic materials where you everywhere you have a crystalline long range order. No, here you have a long range order in particular localized region known as the crystalline lamella. So you can see this is like bricks. So this is like bricks is flooding in the mud. So this mud is like a amorphous matrix. So this is semi-crystalline polymer. And this semi-crystalline polymer, basically, the piezoelectricity, this is arising due to the crystalline regime. So in order to get the piezoelectricity and pyroelectricity, how much degree of crystallinity is there? This is one of the major factors. Okay. So, and once we buy this particular polymer, then you have this particular phase. This crystalline phase, it has different crystalline polymorph. What does it mean? That means it has different crystalline, phase. So one is the alpha phase, and this alpha phase, if you look, this is the hydrogen and this is fluorine. This is the carbon backbone. So as I mentioned, CH2 and CF2, right? This is the monomer. So you see this is a repetition, but there is a rotation of the chain. Here, hydrogen is downside and fluorine is upside. So dipole is up, this side is dipole is down. So it is getting cancelled. Again, here it is up and down, is getting cancelled. So it is non-polar phase. So it doesn't exhibit any electroactive property, meaning that it will not show piezoelectricity, it will not show that, you know, pyroelectricity or ferroelectricity. So in order to get this particular phenomenon, one has to introduce the beta phase. And what does it mean? This is like all trans conformations where you can see all hydrogen are in particular directions and fluorine are in one particular direction, and you see all dipoles are like aligned in one particular direction. So this is known as the beta phase, which is fully polar. So dipole moment is greater than zero here. In the case of gamma phase, these three main phases there. Gamma phase, you can see these three arrow are up dipoles, but one arrow is the down here because there is a gauge defect. So this is known as a gauge defects, and these are like all trans. So triple T G. Here all are triple T. Here T G T G. So triple T G, one is the gauge defect. So this is cancelling it up. So it's still one will get some polarity. So it is known as the semi-polar. So mu is again greater than zero, but it is not fully polar like beta phase. So that's the reason beta phase exhibits a higher piezoelectric activity than the gamma phase. And Then the beta phase is also suitable for non-volatile memory like ferroelectric device, and gamma is a less polar, as I mentioned. So it has another application which is known as electrical storage device, like pulse power based energy device, where you need like camera flash. So at a time it needs the spark. So that kind of energy device, it has the pulse power we called, it has the application. So it also, that means a simple materials which is really cost effective, it has many applications. One is the piezoelectric based application. Also it can store the energy like capacitor, right? So like gamma phase. So the question comes, how can we reach to the this particular phase from one phase from another phase? So one is like, once we buy it, we have a alpha phase. Then we, if we draw it, like we have to give a simple stretching, then we can reach to the beta phase. If we like do any high temperature, then again we can go to the gamma phase and so on. So this is the very tedious process because one has to stretch it, mechanical stretch. Then only one can reach this. And how can we characterize the beta and gamma phase? One simple way is the Ftir spectroscopy. So if we look where this is the new method that we develop, if we incorporate the metal nanoparticle in the Pvda matrix, then we can able to induce the piezoelectric phase. So you see in the black spectra, where you see there is no this particular piece 1 to 7.5 centimeter inverse, but once we put the silver nanoparticle, you can see this peak is rising up, meaning that this piezoelectric phase is getting formed. Here is the another way where we put the gold nanoparticle, and this is the without nanoparticle. You can see the alpha phase is there, but once we put the gold nanoparticle, this alpha phase diminishes and the beta phase is going up, right? So this is the surface morphology. You can see the color of the film because of the surface plasmon, I mean the matter from the gold nanoparticle. And this is the crystalline lamella. You can see needle like structure in between, and there are many particles. These are basically gold nanoparticle is spreading, I mean the spreaded over the surface. So there is another way to make the beta phase, like for the electrospinning setup. So electrospinning setup is a very simple setup, but one has to apply very high electric field between the tip and collector. So this is the metallic collector and this is metallic tip. And if we put the polymer solution here, and if we give the syringe pump this side, and if we apply very high electric field like 10 kV or 20 kV, then if we give pressure here, then you will get a spray. So you'll get the polymer jet. And if we collect this polymer jet, then we can see it is a fiber like structures. You see, this is the fiber like structures. So that is basically spongy in nature, and one can integrate with this the textile because it is air permeable in nature. And we made the Xps spectroscopy. This is just to clarify that in during electrospinning techniques, our materials is not getting disturbed. You can see CH2 and CF2 ratio is like 1:1. As I mentioned in the monomer, there is a CH2 and CF2 unit, so 1:1, right? So from the area under the curve, we can see it is really 1:1. That means during high electric field, our materials is also not getting disturbed. So this is one experimental proof of evidence that electrospinning technique is very good to induce the beta phase. You can see this red curve after electrospinning, this phase is coming out, meaning that we have the beta phase, which is not available in the case of simple solvent casting film. There is a no peak here. So this is one of the good technique to induce the piezoelectric phase. This one I am not discussing in detail, but just to give you an idea that during 2011 we have published this paper to confirm how the dipoles are oriented in the electrospinning technique. So this is the second paper in the nanogenerator field, particularly where polymer is considered. So we missed the opportunity to claim as a first paper due to our negligence, but but this is one of the highly cited paper. Then after joining Jadavpur University, actually, so we have given several approach to make the nano generator, where we use the self pole technique because there is a no polling machine there. So I focused on how can we pole in different way. Ferroelectric nano generator, this is another one. Plasmonic component we have added to get the plasmonic kind of functionality. Then electrospinning nanofiber, this is already we work, so, and then nothing new. But biopiezoelectric nanogenerator, this is something new we did in during my Jadavpur days. So here what we did, you can see, don't focus on these too many results, but if you focus these two, see black, it means no additive is there. In this is only PVDF, but we have added DNA here. So how, and then you can see this particular peak. So what we did, DNA is like this, then we denaturize it. That means we like cut our DNA, by scissor. So we have a single strain, and then there is a lot of surface charge are there, and this surface charge basically interact with the PVDF chain, and there is a electrostatic interaction that give rise this particular beta phase. So we got very nice beta phase once we put denaturized DNA in PVDF solution, and then if we cast it, we got very good phase here. And this is surface morphology. This is some typical characteristics, and then we make the device with a top and bottom electrode, and then we give a pressure. You can see different pressure, we can generate different energy, like 20 volt we reach by 63 kilopascal pressure. So mechanical stepper machine we use, like swing machine and so on. I'll show some video to generate this much voltage. We put different array of LED like ONPDL, you see, and like Jadavpur University JU, and then if we give a pressure, and then we can power up our LEDs. So we have shown we have demonstrated this. This is the typical power curve where we use different resistance in external circuitry, and we measure the output voltage to get the where is the maximum power we are getting, right? Maximum power transfer theorem, we know. In charging voltage, we different capacitor we charge by, this is a bridge circuit, and we put a capacitor to charge via nano generator, and I think I will show a video later. This is another approach where what we did, we make a, the porous materials, and then this beta phase is there. You see how porous it is. You see the nanoparticle is there, and we make the porous structure. This is the in cross-sectional image, and this is some spectroscopy by which we can say we have a very oriented dipole here, and you see very high dielectric constant we have reached. And then this is the device structures. So if we give the pressure, and we can light up the LEDs and so on, we can even light up LCD screen and some wristwatch and so on. This is, I'm not discussing this part again. Yeah, this one I'm not discussing. Yes, so this is basically what we did. Some sensoric application, like what wind vibration response, where we place our device here, and we put a wind flow from different direction, and we again measure the voltage and current, and then we can harvest the vibrational energy. Another thing, like we placed our device in the vocal cord, and we say different words like hello, bye, etc., and then we made a first Fourier transform theorem to check the frequency between male and female, whether our sensor is good enough to sense our voice signal or not. You can see this way we placed our sensor in the vocal cord, right? So once this bodies is closing and opening, we can track the response through this device, and we can again we can make a spectrogram, like like if we speak like ONPDL, then we can see the time versus frequency plot, and this is the amplitude plot. So this way, we are expecting to monitor our voice signal or noise signal in near future. And this is the way maybe we in near future we can say whether people is healthy or have some problem in coughing sound and so on, by tracking the voice signal. So this is the idea that we are working on currently, to check whether we can able to track the people that get affected through influenza or not affected through the voice signal monitoring. So this is the area we are working on. Then again we measure the typical artery pulse. So this is our fabricated device in from Jadavpur University, and we measure our device, then we validate our device with the commercial sensor, I mean commercial device, and then we show our device is very consistent with the commercial sensor. And we found in normal rest condition like 82 bpm, then after physical exercise, like it enhance, and then some students are maybe smoker, so they also check after smoking, and they found, like, it is different from the rest condition for sure. So that indicates, like, this sensor is really responsive to check different physiological condition. Then they make many difficult calculation, like radial augmentation index and many index that can indicate some physiological condition status that I'm not discussing in detail. But the main take home message is our laboratory based materials, by very simple technique we can make, and then we can even track our radial pulse through this device. Only we need a DSO that every laboratory we have, and only magnetic stator, nothing else. And then if we like track our, we placed in different finger, and if we move different finger, because see, each finger has different own restriction to movement. It's like one finger thumb cannot able to move like little finger, so that's the that's the idea to track our different finger movement. And you can see from this signal that the all movements are a bit different from each other. This one again, this is like we address the electrode related issue. I'm not discussing this thing in detail, but it is same story coming again and again. Here only we have focused, like, mainly organic electrodes. So, and you see the in the case of organic electrodes, like we can able long time, like after 6 months also it's showing, very constant output voltage. So it is very much stable in nature. Yeah, so that is one way. This is another interesting work that we did. That is, the fish swim bladder. So I always look to the natural biopiezoelectric materials that time, because of the one of the restriction, another is due to my own interest. So every day we used to go for buying the fish, right, in Kolkata. So you see, this is the swim bladder that people throw it away, right? Most of the cases people throw it away, and then it needs again management system to, waste to put in proper places. So waste management is necessary. So the main idea is, like, it consists of a lot of collagen, and your body and tissue, it consists of collagen too. So that it has very good compatibility with our body, because the bio implantable device, you have to think about the compatibility issue as well. So that was the initial idea to start with this work. And then we check with the scanning electron microscopy, and we found there, some wavy kind of nature, and you can see very aligned nanofibers kind of structures, which is very, very interesting. And if we look a little bit closer here, you can see some wavy structure that is called periodicity. And later we came to know that this periodicity is arises due to the helical structure. It is like triple helix. So we have a collagen, like it is like DNA, but instead DNA is a two strain, right? So here is a triple helix, like মেয়েদের চুলে যেরকম বেনুনি করে, basically it is like that. So is a basically collagen, and it is triple helix, and that exhibits the piezoelectricity. For this, you no need to do electric polling, nothing is necessary. It is a natural source, and you have a very good piezoelectricity. So this is the first article where we have established that it has the intrinsic piezoelectricity, and it has a degree of molecular alignment like 30% without doing anything. So these are the all spectroscopic loops, and this is again some physics like ferroelectric loop and other things, because that was the first work when we convinced to the scientific community that it has the intrinsic piezoelectricity. And that's the reason we did some physics, more typical physics apart from the application oriented things. This is the typical example that every time I'm telling, like, the mechanical based energy stability. If you increase the voltage pressure, you will increase the output voltage, and so on. And this work get attracted through the media, and through, editorial press release. Not only, like, all the media, it came from the editorial. After publishing this, it came through the media. So throughout the world, like, it get interested, even, in different language, different country, like, this is written in the German. So, and like similar like Portuguese and so on. So with this, I'm showing you a very uh, uh, interesting video.
Sound is not coming actually. Video. Sound of the video is not coming. Is there any problem in the sound? Sound is not coming.
Okay. Let me check, sir.
Okay. Okay, please check. Intermittently it is coming, but overall it is not coming.
Sir, it is coming.
No. No, it is not coming.
Well, fish scales, along with bones, cartilage, and tendons.
Now it is okay. No, again same problem. Not coming. Probably sound level is to be enhanced slightly because some noise is coming, but not the actual sound.
No, we can understand more or less.
Right.
Dr. Mondal, you have 15 minutes.
Yeah. So this is again is it's okay.
Okay.
Yeah. So let me conclude this. Yeah. So you see, this is basically pressure mapping by bio-piezoelectric nanogenerator, where we arrange our the sensor in such a way so that if we give a pressure like this, let me use my pointer. Yeah, like this, you can see the pixel. So similarly, if we give a pressure like O, so N P D L. So we can really make it like the pressure distribution according to our the shapes, and these are the students those work on this. And this is my first part. Second part, I will go very fast, so don't worry about the timing. I will complete it within the time. So because most of the part I have covered in the first slide and the basic parts. So yeah. Mm. So can you see this now?
Sir, PPT is not visible right now, sir. Yes, sir.
Not
Yes.
visible?
Yes, sir. Now
Yeah,
it
now
is.
visible?
Yes, sir.
Yeah. So pyroelectricity, right? I talk about the pyroelectricity here. So again, is a way to harvest the thermal energy basically. So instead of mechanical energy, and if you see, this is very old phenomena where kind of uh, yeah, 24th centuries, right? So even in much higher than the piezoelectric things. And you can see there are some natural crystal that attracts the wood shaw and so on. This is some history where we can see the main interesting thing is like the Röntgen, Curie, Liebman, Owens and Schrödinger, Martin and Max Born. These are the scientists. They are famous in their own field apart from the pyroelectricity, but they are the people, they wrote the paper all together for the pyroelectricity in 20th century. So this is very interesting, one can read this paper. But yeah, let me show you the main reason of the pyroelectricity, what is the basic. So the pyroelectricity basically the way of thermal energy harvesting. Okay, so it is like if we have the temperature fluctuation. Are you getting my voice clearly?
Yes, sir. Your voice is audible,
Yeah,
sir.
okay, fine. So this is the basic principle that we have to know, then we can do a lot of things. So it is basically temperature energy harvesting, thermal energy harvesting. And there is a difference between the pyroelectricity and thermoelectricity. Thermoelectricity, as we know, it need a constant temperature gradient, like hot junction and cold junction. So there is a constant temperature gradient. Whereas in the pyroelectricity, you have to make it the temperature fluctuation, off and on, off and on. So this kind of environment, we can get the pyroelectricity. So this is the basic difference in the case of the pyroelectricity. So we discussed the pyroelectric coefficient. We can go each from one thermodynamics parameter to another. There is a pyroelectric coefficient as well. These are the materials, but most of the cases, those are like exhibits the piezoelectricity. They also exhibits the pyroelectricity. So this is the diagram. So this is the dielectric materials. So some of the dielectric materials are piezoelectrics, some of the piezoelectric materials are the pyroelectrics, and some of the ferroelectric materials are the piezo-pyro both. So if you choose the ferroelectric materials, then they essentially shows piezoelectricity and pyroelectricity together. So that's the main idea to choosing the materials. So the major application, like recently we happened a bomb blasting in different country at the night time. Then thermal camera is important, right? And now we are getting much familiar with the thermal camera because of the COVID issues. So that basically infrared, it needs an infrared camera detector, and this is the many satellite cases where infrared detectors are necessary. Then the question comes, how can we make it the temperature fluctuation? So there is a chopper is available, rotating chopper, and this is the array of the pyroelectric materials. And this is basically a schematic that how can one can make the infrared detector. And this is the image. You can see one can take photographs during the night time. So this man is walking, car are coming, and this is possible to catch up. Here also we can see the one man is crossing the roads at the night time. So, and this is my colleague, and who is we take tea together, and you can see I am the taking tea, but he is busy with his mobile. So this is the idea or use of the pyroelectric based devices. So since it is basically same, those are piezoelectric, they can exhibit pyroelectric. So that's why some of the slides are very common. We make the pyroelectricity. How can we enhance it? So we use some RBM, because RBM has infrared absorption capability much better. We make a porous film. It is known as the electrode, and some physics are there. And then we make the pyroelectric sensor. You can see here we put the temperature like off and on. This is temperature signal, input signal, where delta is 14 Kelvin. Here we increase the delta 24 Kelvin, and this is the rate of change of temperature, is the first derivative. And then this is the basically we measure the current. So this is response from our device. So we put an infrared bulb, and through the relay circuit we can make it off and on, and we can use a Peltier cooling here to make it to lower temperature. Then we can charge up the batteries, we can capacitor and so on. So this is the laboratory based work we published in scientific report. This is another application. You see your finger, right? So each finger has different energy, area, or let's say thermal gradient, little ring, middle, index, and thumb. And you see the response of the voltage or current is different as well. So that indicates your temperature gradient can able to sense this sensor very nicely, right? So that's what we did here. And this is electro spinning based some sensor we make very similar way. This is more attractive since in the COVID era, and this we published in 2017 or 18, and before this happened, where we placed our pyroelectric generator here, and if we breathe it and breathe out, we can able to again measure the temperature, or in terms of, let's say, temperature here, or also in terms of voltage and current. So this is the kind of marks we can use from the breathing. We can power up our device, or we can produce some sort of energy. Recently we have made another contribution in related to face masks, where we use the triboelectric phenomena, and in order to filter out this kind of issues. So with this, I want to thanks my students and all of you. And if you have any questions and queries, I will be very happy to discuss. So with this, I'll stop here.
So it is open for question answer session. So if any participants have any question or want to know any information, please post your question or drop it the question in the question answer section. So we invite all we invite all the participants to kindly ask question, or they can ask any information related to the session. Please.
Otherwise, I have a only sound problem. Otherwise, I have a few more interesting video clips I can show.
You
Yes,
can
I think
show.
I think you can show.
Okay, okay, sir. Okay, okay.
Sir, the screen is not visible if you are sharing anything, sir.
Hello, hello.
Sir, screen is not visible. Are you sharing something in the screen, sir?
Okay, okay, okay. Then I have to share, right? I have to,
Yes,
okay,
sir.
Yes,
okay.
yes,
Yes.
yes. First you have to share.
Share. Okay. So, sir, now this is okay.
Yes.
And
Now it is okay. Yes.
yeah.
But sound is not coming till.
Yeah, because some problem. So that's the problem. So not at all. You are not getting any sound, sir.
No, no.
Oh, sometimes we are getting some sound.
Oh,
Sometime a little bit is coming, sir.
Little, little.
oh,
I think you have to put the mic in front of the speaker.
speaker.
More closer, yes, sir. More closer. So kindly make the volume increased and keep the mic in front of the speaker.
Let me wait. Wait, hang. So is it visible now? No.
Is
Yes, visible,
sir, but not audible.
but sound is not coming.
Oh.
Audio sound has some problem. Audio has some problem.
Sir, if you have the link of the video, then you can pass it on to us and we may let the video display from here.
Okay. Yeah. That I can
If
do.
you have the link of the videos, yes, sir.
Yeah. So what I can do, I can send the link. Okay. Because it
Yes, sir.
is in the YouTube. Okay.
Yes, sir. We can play from here if you
Yeah.
provide us the.
Okay. Yeah. So I'm just going to email you then.
So you can post it in the chat box also, sir.
Oh, it's possible. Okay. Yeah. Oh, let me check. Fine. So, sir,
Yes, sir. One link
yes,
I have received, yes, sir.
yeah. So you just click on it, and then you have to stretch to the end to make
Okay,
it.
sir.
Yeah.
So you just asked me what the things to be done.
Yeah. So you start it. Yeah. So I send you the link, right? Okay, fine.
Is it visible, sir?
Yeah.
Yes. Okay, now it is okay.
Hello and welcome to a fresh new episode of Science Monitor, our weekly update on all that is happening in the field of science and technology in and around the country. From launching 8 satellites together in 2 orbits to generating energy from fish scales, Indian researchers have made it to the headlines this week with many stunning scientific feats. But before we get on to the details of what these achievements are, let's take a look at the headlines first.
Yeah, so
CSIR
now,
and
yeah, you
platinum
stretch
jubilee.
into some up to middle.
And
an angle of 98.2 degree to the equator.
Then after this, maybe, yeah, after
The
this
several
stop.
satellites were further deployed in this orbit in a predetermined sequence. In the coming days, SCATSAT-1 will be brought to its final solutions to common problems. That was what the first BRICS Young
Yes,
Scientists
after
Conclave
BRICS,
was
you will get.
Yes, sir.
After BRICS, this news you will get.
about. The first BRICS Young Scientists Conclave was organized by the Department of Science and Technology in collaboration.
What we believe is that instead of each one discovering the wheel, we jointly do that. And in the past, this has also always helped.
The conclave was focused mainly on three themes, including computational intelligence, energy solutions, and affordable healthcare, along with discussions on interdisciplinary science for society and humanity, a scientific journey for BRICS, traditional science and indigenous knowledge, and science, technology, and social equity. Along with young researchers, the conclave saw the participation of more than 20 renowned researchers, innovators, and entrepreneurs from BRICS nations.
They are already doing science, some of them are developing technology. Can they do something at a level which would make a difference to the bottom of the pyramid? Would they make something very innovative which would transform the world? That's our idea, to trigger them. And I'm sure that something would trigger in their mind and go with confidence that if some people could do, I could also do. Maybe I could do even better than the person who spoke to me.
The conclave was aimed at building a BRICS Innovation Corps with specialized skills to work on novel scientific ideas and technological solutions for social transformation. The conclave is expected to pave way for creation of strong generation of science and technology leadership that can accelerate change collectively. The conclave also included during India's chairmanship of BRICS in 2016 under a focal theme of building responsive, inclusive, and collective solutions. The conclave is an initiative under the BRICS Young Scientists Forum, which was formulated at the second BRICS Science, Technology and Innovation Ministerial meeting held at Brasilia in March 2015.
while fishes as a food are a hot favorite to many of us, so will be the fish scales now, as Indian researchers have come up with the most innovative use of discarded fish scales. Yes, it would now be possible to harvest energy from raw fish scales. What is more, researchers are even planning to scale up the use of fish scales to develop new generation pacemakers.
Indian fondness for fishes is known worldwide, and large quantities of fishes are consumed in India every day. What if the large amount of waste generated from fishes and fish processing could be used to generate energy? Sounds far-fetched, but this is exactly what a team of researchers at the Jadavpur University in Kolkata has done. The team comprising Sujoy Kumar Ghosh and Deepankar Mandal has developed a technology to recycle fish scales for self-powered electronics. The technology is based on the principle that raw fish scales contain collagen fibers that has piezoelectric property. As a result, they can generate an electric charge when a mechanical stress is applied.
We found the fish scale is one of the good source because it is a waste product. So we used the fish scale directly to make it the devices which can give rise some sort of power. We named as the Nano Generator. So In particular, we more specifically it named as Piezoelectric Nanogenerator because Phi scale is basically biopolymer, we can say. It is like a natural source which have the inherent piezoelectricity, and we can very simple process, we can able to fabricate a add value product which has the emerging the industrial applications.
During the study, the researchers first processed the raw scales obtained from fish processing markets to make them flexible and transparent. Following this, 2 electrodes were attached to each scale and laminated. It was observed that the resulting cells could harvest energy from movement and mechanical stress around it, including simple motion-like vibrations and heartbeats. The new technology called Piezoelectric Nanogenerator has many potential applications in future. The scope includes scaling up the technology to power pacemakers. Once implanted, such a device will be able to continuously power itself from heartbeats and will be able to degrade when no longer required. The research published in Applied Physics Letters opens up new and exciting avenues of green research which can aid environment by making use of biological wastes to generate useful technologies.
I think that's it, sir.
And now it is time to take a very short break. We'll be back with more science news.
Sir, shall I go for second video?
Second video you can check, but this is for different, of course, it is a different topic, but similar.
Sir, you have to give the instructions, sir. So I will follow.
Yeah, second topic you can check. Yeah, very fast. You can just move forward.
Yes, sir.
Same way. So these basically from Rajya Sabha TV. They only select if the work is selected by particularly editorial, press release kind of thing. So they came to us.
Hello and welcome to a fresh new episode of Science Monitor.
Sir, from which part, sir, starting or
Yeah,
sir?
you just move forward. You will get. Say, I will tell you where to stop. Because there is some forest fire that time in Himachal, and then after that the story will start. You can take a look. You just move forward.
Yes, sir.
Position to get burnt next year if such kind of human error or even climatic variations happened, or there is no
Added to this is the fact more serious consequences. Rapid melting of state.
Hassle, especially while we are traveling. But
Yeah,
now
this
it
one.
is time to say goodbye to plug points and mobile chargers, as
Just
researchers
1
have
second.
come up with a technique to charge mobiles using body movements. The technology has been developed by scientists at the Jadavpur University in Kolkata. The team has developed a DNA-based nano generator which can convert the energy of body movements to electricity. Let us see this report.
No one can deny that mobile phones and portable tabs have made communication and many other activities of day-to-day life much easier. Hassle comes when their batteries run out fast and one gets into a fix finding a charging spot, especially during travel. But what if we could completely avoid plug points and power packs and depend upon our simple body movement to charge our phones? Yes, this may now be possible with the super smart DNA-based nano generators developed by a team of researchers under the leadership of Dr. Deepankar Mandal from the Organic Nano Piezoelectric Device Laboratory, Jadavpur University, Kolkata. The team has developed a novel kind of nano generator using a biocompatible polymer film made out of polyvinylidene fluoride or PVDF.
Our idea, if we can able to make it the self power, because this nano generator is so sensitive, and we can take the energy from our everyday motions, from the living environment, for example, from walking, talking, even from the blood flow and wind and any sorts of energy, because it is ultra sensitive to the vibrations. And as our portable devices is becoming smaller and smaller, so the requirements is power is also smaller, and that can be fulfilled by this kind of generators, mechanical energy harvester, we sometimes say.
The device is based on the science of Piezoelectric Effect, which refers to the ability of certain materials to generate electricity in response to applied mechanical stress. The generator can harvest energy from everyday motion, like tapping a phone, and turn it into electrical power. To add to the efficiency, the researchers have incorporated DNA into the device, which, due to its ability to conduct electricity, increases the energy harvesting ability of the device. The team has demonstrated that the device can be powered with gentle tapping and can light up 22 to 55 light-emitting diodes. Going a step ahead, the team has further designed novel nano generators using cellulose, the most abundant biopolymer on Earth.
As our materials made with the piezoelectric materials, I mean the flexible piezoelectric materials, so our device, you can able to fold it, you can place into your shoe, and you can walk, and you can generate some sort of power, and that eventually you can use for your mobile phones and any sorts of portable electronics that you want. So it is very, very useful.
The team has come up with a novel material by mixing cellulose with a kind of silicon called polydimethyl siloxane and carbon nanotubes, which can be used to charge body implants and biomedical devices. Using body's internal stretches, vibrations, and other movements like heartbeats, blood flow. The research that has been published in the journal ACS Applied Materials and Interfaces opens up a new area of novel energy storage devices that are more efficient, environment-friendly, safe to use, and most importantly, biodegradable.
Yeah, I think that's all.
Yes, sir.
Okay, so we thank Professor Dipankar Mandal for a very interesting and engrossing talk on a very exciting topic. And if there are any questions, the participants are encouraged to ask questions. If there are any questions, then please ask.
For participants, if you have any questions and you want to know any information related to the topic, please post it in the chat box or in the question answer section, and we will be very soon moving to our next session. Participants, if you have any questions, please post it in the chat box or in the question answer session.
Till now, there is no question.
Okay, so Professor Bhatt, do you have any questions?
I don't have any question, but I can thanks to Dr. Mondal for giving such a nice lecture and elaborating almost all levels, means how synthesis to delivery level. Delivery means nowadays it is very important that what is giving delivery to the society. He has shown that how this material important and how it can be utilized for the human being. And several ways he has put his experience not only in the laboratory but in the actual system or actual uh, for people, for the society, how it can utilize in for particularly in crisis of energy, or at least small energy where input or current is not very large. In that case, it is very useful. He has already shown several applications that when movement is there, so small movement is there, whatever may be the movement, that can also generate the requirement. In some cases, that requirement can be fulfilled by generating electricity by the way by which what they have generated. Way by it is very important in application area point of view. It is very important, particularly in the situation of crisis of energy. Means he has already pointed out, all the people are pointing out that within next 10 years, we are going to have huge crisis in fossil fuel. So to replacement is needed, and he showed some such example. The utilization point of view, he has showed some of the areas which is maybe utilized where power requirement is not so high, but total requirement may be not small. And not only that, that should be user friendly, and also waste management point of view, that is also very important. So thanks to Professor Mundal for
Thank
giving
you.
your valuable time for our participants, for our university. I thanks to you on behalf of our organizing committee, on behalf of the university, of Maulana Abul Kalam Azad University of Technology, for coming over here, joining with us, and spending around say around more than around 2 hours for our participants, to giving or highlighting the different area in which uh, what are the work going on, and what your contribution for the initially you started with survival means how we can survive in the university, because university resource is very minimum.
Very
Even
important,
that's
sir.
we okay. In some cases, nothing is there. Nothing is
Yeah,
there. So how with that
yeah,
how we can start? How we
yeah,
can start? And I have seen that good number of students are with him. Say always
yeah,
8 to 10 students are with him, and most of them are came from different levels. In some cases, they are in the first generation education they are taking. I have seen, and all level of students he has taken. So with giving them training, and they are coming up to the level of PhD, means highest level of degree. So that is a good thing that he is doing for the not only in the way of scientific, but also for the community. He is giving the service to our general people. So thank you, Dr. Mondal, for
Thank
coming.
you, sir. I have a small announcement. Small announcement.
Okay.
Since the participants are basically nothing but our colleague, right? So if they can also encourage the student to come to Chandigarh and to work with us, because it is a new institute and a lot of resource. All facilities are available with us, from XPS to XRD to TM to AFM. So, and I am the in charge. So any sample you people send, I will make sure I will give you free of cost. Please, you send your student to us. That's the only condition.
Okay, thank you for giving this opportunity to our students and also participants. So
Yeah.
many thanks on behalf of me, on behalf of our university. So thank you very much.
Thank you, sir.
And okay.
Thank you again, Professor Mondal.
Thank you, Professor Sanal. And I think we will have a future communication.
Yes, yes.
For,
We hope to have
Sure.
you in our meets sometime later.
please take care. Yeah.
So, we move on to the next speaker.
Bye.
Right. So we move on to the next speaker, who is Dr. Shilarita Sengupta from IIT Roorkee. So I will just introduce him in 2 minutes. So, Dr. Shilarita Sengupta, he did his PhD from Jawaharlal Nehru Center for Advanced Scientific Research in 2013, and he was a postdoctoral researcher at the TIFR Center for Interdisciplinary Sciences, Hyderabad from 2013, and he was a postdoctoral fellow at Weizmann Institute of Science, Israel from 2013 to 2016, and he was a postdoctoral fellow at the University of Tokyo, Japan from 2016 to 2019. And Dr. Shilarita Sengupta is an assistant professor he joined as assistant professor at IIT Roorkee 2019, where he is continuing till present. Okay. So the title of Professor Shilarita Sengupta's talk is Classical Molecular Dynamics Simulation as a Tool of Modern Day Physics. So with that, I leave the dais to Dr. Shilarita Sengupta. Whenever is it. Your voice is not
Kindly
audible.
unmute your mic, Shiladitya
Okay.
sir.
Yeah. Am I audible though?
No,
Yes.
make the
Yeah,
volume.
Now audible. Now audible.
Now, yeah, I just realized I started without unmuting. So thank you, Professor Sannal, for a nice introduction. And I would like to start by thanking the organizers for having me here. So shall I start now or shall I wait?
Okay, you can share. You can share
Okay,
the screen.
okay, I'm going to share the screen. Is it visible?
Yes, yes.
Yes, sir.
Yes.
Okay. So I realized that in West Bengal, so as Professor Sanal mentioned, I come from IIT Roorkee, Department of Physics, and IIT Roorkee is not so well known in West Bengal, it seems. So I start by giving a quick introduction to our institute. So Roorkee is somewhere between Delhi and Dehradun in Uttarakhand. So this was the first modern engineering college in Asia, established in 1847, and it became an university in 1948 and upgraded to IIT in 2001. So currently there are maybe 21 or 22 departments which covers everything from engineering, science, humanities and social science, and even management. So I guess except medical college, we cover everything. There are also few centers of excellences on like Nano Center and some hydrology center, etc. And also some there's a startup incubator called Tides. I think right now there are more than 500 faculties across all the disciplines and 8,000 plus or 9,000 students, and the number of students is going on every year. So I come from physics department. So currently there are 35 faculties, and most importantly, there are a lot of young faculties, and we are now recruiting in all areas of physics. So you can be part of the department at various levels. Like you can come for a postdoc as a national postdoc fellow, or even institute sponsored postdoc fellow. There are PhD programs, so PhD admissions happen twice a year in high energy, condensed matter, photonics, electronics, applied physics, etc., nuclear physics. There are a couple of MTech degrees in solid state physics and photonics, and a 2-year JAM, meaning 2-year MSc through JAM, and a very successful BTech engineering physics degree. And of course, recently there is this summer student program, which so the summer students can come to IIT with some fellowship called Spark, which is offered by IIT Roorkee. So now let me tell you a little bit about my background. So I work on amorphous materials, which is broadly part of soft condensed matter physics. So as you know that most of the materials in daily life are amorphous. And so this slide shows, so let me see, sorry, how can I share my, how can I show the laser pointer? Can you see the pointer here?
Oh. Yes, I can share. I can see your pointer.
Huh. So how do I show the laser pointer? Is there an option? Okay. Okay, let me. Okay, anyway, I will use this pointer as it is. So please bear with me. I'm sorry for the trouble. So what I wanted to show you is that if you look at this slide, this picture, so in this picture you have a wide range of materials. All of them are amorphous materials, and they have a wide range of length scales of the basic building blocks. For example, if this is the metallic glass, which is used in the mobile phone screen, and the basic metallic basic building blocks are atoms, which is at the nanoscale. And on the other end, you have these granular materials like sand particles, which are the building blocks. The particles of sand will be a millimeter scale or even bigger. So this covers a whole range, a big range of length scale. And so I study various mathematical models which mimics some of these materials, such as
What happened?
materials. Yes, sorry.
Okay, fine. Let's start.
Okay, so I study mainly structure and dynamics of this kind of material to understand various natural phenomena, such as the physics of glass transition and the jamming transition. And as part of the study, I use molecular dynamics as a tool. So okay, so I was told by the organizers that the audience of this program will come from various backgrounds of science and engineering. So what I had in mind as a target audience, or the ideal audience of this talk, is someone who, let's say, is a postdoc who has no previous exposure or background in molecular dynamics, but wants to planning to use molecular dynamics as a tool and starts to do some research using molecular dynamics. And so the talk is pitched for at that level. So to give you a crash course in MD, to sort of give you an idea of what it is, what it can do, what it cannot do, and help you to enable you to sort of learn further and start working. So the talk is the plan is to divide. So the talk is divided into these following sections. So first, I will tell you what is MD, and in particular, I will tell you what is a particle-based classical molecular dynamics simulation. So I'm going to explain all the terms. Next, I will tell you why using MD. So what are the opportunities of MD as a tool for, so I said here is a modern day physics research, but some of these points will be relevant for chemistry and other science disciplines and other engineering disciplines as well. Then I will walk you through a model MD code to sort of give you an idea about the inner workings of a MD simulation. And I hope that with that knowledge, you will be able to appreciate the some of the limitations of MD as well. Then I will give you some further references, textbooks, and softwares that you can use and learn further. And finally, I have a couple of slides as a kind of a case study. So I will give you a concrete example of a project where you can where as a kind of an application to show the application of MD in real cutting edge research, and which was possible. The progress was possible mainly by molecular dynamic simulation. So let's get going. So here I show you a snapshot of a system at a time t. And what you can see is a bunch of balls inside box with walls. And so the basic question of any simulation is that if I give you a state of the system like such as this at a time t, can you guess the state of the system at a time a little bit later, like in a t plus delta t? Now, of course, the underlying microscopic rules of equation of motion are completely time symmetric. So you can also ask equally that what was the state of the system at a time t minus delta t in past, which leads to this the present state. So there's an equivalence questions, but by convention we usually focus on given the past, present, what you can, how can you guess the future? Now note that this question you cannot answer because I haven't told you what the system is, and which means that I haven't told you what is the underlying dynamical rule, the update rule. For example, is it a kind of a simple cricket ball colliding with walls, in which case they will follow simple classical dynamics like Newton's law of motion, or it could be some electrons inside the box, in which case you want to solve the Schrodinger equation of motion. Or given the current scenario, one other highly relevant scenario is that suppose this is a simulation of lockdown of either the balls represent either people or a community or a city or a state or a country in a lockdown, and you want to study the effectiveness of the lockdown, in which case you have to use some kind of a ACIR type models for disease propagation or something complicated. So the point is that so you need to choose your dynamical rules. Now, by the way, if you are wondering what is this system, this is an example taken from a computer game, which is part of Linux, simple computer game of balls and collisions, etc., which is actually an example of MD simulation. So, okay, so how do you choose these dynamical rules? So, of course, this will depend on the particular system and the natural phenomena that you are going to study. So, for example, and you can, one simple way to sort of decide is to use the fundamental constants of nature. So here we have these three constants, the Planck's constant here, h bar, the speed of light, c inverse, and the gravitational constant, g. And so we have plotted them as three different axes, and along each axis they can have value either 1 or 0. So h cross equal to 1 means the quantum effects are going to be important, and h cross equal to 0 means you can safely ignore the quantum effects. Similarly, 1 by c equal to 1 means that it's a relativistic scenario, and c inverse is 0 means you can, it's a non-relativistic situation. And g is 1 means the gravity is a strong effect, so you have to use these nonlinear equations of GTR. You have to use Einstein's theory of gravity, whereas G0 means it's just a normal Newtonian gravity. There is no non-linearity in it. So the world of classical MD, so the meaning of classical means we are situating at the origin. So there is no quantum effect it's a non-relativistic and no GTL. So this is the domain of non-relativistic Newtonian mechanics, and this is the domain where I am going to the subsequent part of the talk will describe this particular domain. So note that this particular construction, which you can call the physics cube. So the purpose is to show that at different corners of this cube, you have different theories, different theories that describe nature, and each theory has their own dynamical rules. So you have to choose which rules you are going to use. Now, even when we say that okay, we are solving Newton's laws of motion, but even then it is not enough, because the actual choice of dynamical rules will be governed by many other factors. For example, length scale. So consider this famous falling ball experiment. So here on the leftmost figure, you have Mr. Galileo, who is dropping a cannonball. And as we all know that the dominating force is just gravity, and the ball is going to fall along a straight line with constant acceleration g. Now the key point here is I want to highlight is that the size of the ball. So it is of the order of 1 meter. Now if you reduce the size and make it, let's say, of the order of 1 millimeter, so 1,000 times smaller, then the air resistance is going to be important as gravity. And you have to include the effects of air resistance, like for example in the case of if you want to analyze the raindrop motion, and in this case the nature of motion will change completely, in the sense that the drops are going to fall in straight line, but now with a terminal velocity, with a constant velocity. And if you are going to let's say you reduce the size of the particle even smaller, even 1,000 times smaller, so now the particle size are of the order of 1 micrometer, such as the suspended particles in Delhi's air. And now the dominating force are actually the random collisions with air molecules. And the nature of motion is now even much more different. So now these particles are not even falling, they are doing random walk or Brownian dynamics. So the take home message here is that the choice, you have to choose your dynamical rules by fixing your energy scale, length scale, and time scale. And here is the summary of the picture that I want to give. So what I show here is the x-axis is the space axis. So for simplicity, I have put just one dimension of space, and y-axis is the time. So what you have is that a certain size so of the system. So you choose your certain system size or the length scale, and that is going to be your simulation box. And you are going to observe the system for a certain time window. So you also choose your time scale, and that defines your simulation box. And now you put a bunch of particles inside that box. So that gives you the state of the system at, let's say, t equal to 0. And you define your dynamical update rule, which will give you the the state of the system at a little bit time delta t later. So this is the premise of the particle-based classical MD. So now I come to the next part, which is why do MD? Now the answer to this question is since I come from condensed matter physics background, so my answer is going to be biased towards condensed matter physics. And in condensed matter physics, you can broadly say that there are two big goals. One is to predict the properties of materials. Some of the materials may be completely new materials. And second, to understand phenomena on a molecular scale. So for example, here is a quote from Dan Frankel, who is one of the giant in this field. So said that the big question, or the question, is can we predict the macroscopic properties of many body systems. And as we know that there are, in modern physics research, there are three approaches to answer this question. So one, you can do experiment, second theory, and third is simulation. So in experiment, what you do is that you can directly probe the system at various length scales. The job of the theory is actually to identify the basic rules and make toy models to predict different properties, and also to come up with smart tricks for calculation to sort of simplify the process of research. The simulation is actually somewhat in between the theory and experiment, in the sense that in simulation, at one hand, you can test the predictions of theory. In that sense, it is geared towards theory. On the other hand, it can also complement experiments because you can directly visualize the system at molecular scale and calculate various properties. So I want to explain this point in a little bit more detail. So let us see that what one can do in experiments. So this table gives you a few example properties which are taken from soft matter physics. So the first property is so we want to study the structural information about the system, and which is usually done by various scattering techniques, and by which you extract the two-body structural correlation functions like structure factor and pair correlation function. We can also be interested in knowing the short time or the vibrational dynamics of the system, which again are usually done by scattering and spectroscopic methods, and by which we can calculate the density of states, which gives you the vibrational frequency spectrum and tell you about the state of vibration or the normal modes. In soft matter, we are particularly interested in understanding the long time or the structural relaxation, which is a long time process, the dynamics at a long time, which again can be done by scattering and spectroscopy, and also by various rheological techniques. And there you measure the 2-point time correlation functions and elastic modulus, viscosity, etc. And you can also do thermodynamics by, for example, the standard technique is called differential scanning calorimetry, and you can measure specific heat, enthalpy, etc. So all these properties of the system you can measure by experiments. So then the question is that, okay, if you can do all these things by experiments, then why you need a simulation? Now I'm going to give you three answers to this question. The question is that how does simulation complement experiment? So the first answer is there are some conditions where, the goal, or what I wanted to tell you is that where the MD is actually meaningful, useful, and relevant, and complements the fit with the simulation, with experiments. So the first condition is some situations which are either difficult or impossible to create in experiments or in laboratory. Here is an example of that sort of situation. So suppose we want to find the composition of Earth's core and the mantle. So it is composed of various minerals which are subject to high pressure and temperature. And the question is, what are the structures, or what are the crystal structures? Now, obviously, this is a very difficult to do experimentally, but here people have shown that MD simulation can be very useful, because all you need is the molecular formula and the condition of temperature and pressure, and then you can predict the crystal structures. So, for example, here is an example which is the predicted crystal structure of some mineral, probably calcium carbonate, which is present in Earth's inside. The second point is that the in experiments till date, if you want to analyze the structure, it provides only a limited knowledge about the structure, and can only probe structures at a two-body level. Whereas in MD simulations, you actually have everything. You know the positions of all the particles, their velocities exactly, and that give you a very detailed knowledge about the structure of the system. So you can easily analyze the many-body structural correlation. Now here is an example of where it is useful. So this so this snapshot is actually taken from experiment. It's a colloid, supercooled colloid. So colloid is one case which is very similar to experiment in the sense that you can actually measure the positions of all the individual colloid particles and and record them by video. So it is, in that sense, it is very similar to doing a computer simulation. And I was told that is by a colleague of mine that nowadays there is a technique called atomic scale tomography, which actually give you a photograph with atomic resolution of various materials. For example, in India, in IIT Madras, they have a set of instrument for doing that. But this technique is supposed to be very expensive. So, for example, he says that one photograph can cost you 30,000 rupees. So, obviously, this is not useful for many purposes. And in that case, MD simulations can help a lot. So, let us explain this picture. So, so what you see is various particles, and in this condition, it's a very low temperature and high density. So, it's a very crowded environment at a very low temperature. And in such a condition, what you see is that there are slow particles and fast particles. So slow moving particles and fast moving particles. And the slow moving particles are clustered together, and the fast moving particles get clustered together. And what they highlight is two of the slow moving clusters. And so this phenomenon is called dynamical heterogeneity. So this was actually discovered by molecular dynamics simulations. And you can easily see that if you want to understand how these clusters are formed, what are their size, how long they live, how they dissolve, etc. Then doing an MD is very useful because you can analyze them in various details. And you can also sort of appreciate that, suppose I want to know how the individual particles are moving in such a crowded environment. And this is like a traffic jam situation where one individual particle cannot move. So many particles has to coordinate together so that the whole cluster move, or all of them can move. So this is called a collective motion. And in this case, in order to understand those collective motion, you cannot use two-body quantities. You must analyze many-body structural correlation. And in that case, MD simulation is going to be very, very useful. And this is the third point, is that MD simulations can identify macroscopic mechanism of various physical processes. And I just already gave you one example. And here I deliberately sort of put a collage of different examples taken from the LAMPS website. So I'm going to tell you at the end what is LAMPS. So this sort of give you an idea just to that there are a wide range of physical processes in which molecular dynamics are routinely employed to sort of understand various microscopic mechanism. So it ranges from lipids in water to polymer to silver nanoparticle to polythene and to granular materials. Also the dislocation dynamics of crystals, fractures, and whatnot. So with that background, So now I am going to tell you more about the MD code. But before that, there is just a side remark. So you may think that computer simulation is a recent endeavor, but it is actually not. So what I show you here is a kind of a broken slab which was recovered from a Roman shipwreck uh, about 100 years, and yeah, about 100 odd years back. And for many years, people are puzzled by the meaning of those slabs. What are they used? So they know that they were part of some machine. And about recently, like about a decade ago, people have finally figured out what this machine was. And they say that this is a mechanical computer. So it is a computer which was made of balls and gears, wheels and gears, and its purpose was to simulate planetary motion. So so because to sort of predict eclipses, the precise date of eclipses for various religious purpose probably. And note that this computer was dated to 150 BC, which is more than 2000 years back. So, so the first point here is that the computers are very ancient tools. Ancient computers and simulations were even there in ancient world. And second is that, as always, that uh, the 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 astrophysics are always at the cutting edge research at any time. Now, in the 19th century and in the first half of 20th century, up to like World War II, II, there were actually people whose job was to do numerical computations, and they were called computers. So here is a photo of Radhanath Sikdar. So you may remember that he was the first person to compute the height of Mount Everest. So he started his career in the Great Trigonometric Survey of India as a computer, and he retired as the chief computer. So it's kind of amusing to know that the meaning of computer were completely different in those days. And you may also be interested to know that after retirement, he became a professor of mathematics in the Scottish Church College in Kolkata. Now, of course, and this is a slide and another short remark about the birth of the modern molecular dynamics simulation. And this was, of course, possible after the discovery of transistor in 1948, and after which the electronic computers became possible. So this is the first ever paper on MD, which came in 1959. And if you read the abstract, it says a method is outlined by which it is possible to calculate exactly the behavior of several hundred interacting classical particles. The study of this many-body problem is carried out by an electronic computer which solves numerically the simultaneous equations of motion. So this is basically the definition of MD. And here's a picture. So this paper, the authors were Barney Elder and Tom Wainwright, and you can see them in this photo. So this is Elder and this is Wainwright. And one interesting point to note here, you can also find a lady in this photo. So her name is Mary Ann Mancy. So her job was actually to write the code and do the calculation. So probably she was the computer in that sense. And note that she was not an author of this paper. So this tells you about the work culture of those days, probably. And I also want to mention one other fact is that in the field of molecular dynamics, Indians have played a pioneering role. So here I show you a photo of Anisur Rahman. He was from Hyderabad, and he was one of the pioneers in applying molecular dynamics to calculate the properties of liquids. And even today, the highest prize in computational physics awarded by the American Physical Society is called Anisur Rahman Prize. And here is another pioneer, Luc Verle. So you will find his some of his contribution in later part of this talk. Okay, so now we come to the section where I will walk you through an MD code, a very simple MD code. Now, first, some remark about the philosophy of writing a code. So, a well-designed code, you think it like a Lego. You know, this is a picture of like these little bricks. You can join them and make various figures. And so, the basic design of a well-designed code is like one task, one piece, and different tasks, different pieces. And then you have to connect them so that the whole thing can function together. Now, the MD code is simplest in the NVE ensemble, which means that you fix the number of particles, the volume of the system, and the total energy. Under that situation, a basic MD code has just 4 pieces. So here are the 4 pieces. So first you have to specify the state of the system at t equal to 0. Then calculate forces, and from the forces you get the acceleration, and then you update the position and velocity. And finally you calculate various observables, which are the actual quantity that you are interested in. So first is the initialization. It basically means to specify the positions and velocities of all n particles at t equal to 0. So note that we are talking about classical physics, so you can specify both position and velocity at the same time. Now, in order to do that, you need some background information. So first you need to know the state point, like which means the density or the volume and the temperature of the system. And even before that, you need to choose one other parameter, which is the dimension of the space, which can be a 2-dimensional system, which are used for studying thin films or surface, or a 3-dimensional system if you are studying bulk materials, like the properties of the material inside the bulk of a system. So let's first start with the velocity. How do you assign velocity? It's very easy, because you know the statistical mechanics says that if the system is in equilibrium at a temperature T, then the velocities will follow Maxwell-Boltzmann distribution. So it doesn't, no matter what the details of the material, which material it is, the velocities are going to follow Maxwell-Boltzmann distribution. So just to recall, so this is a distribution in which your average velocity is 0, and the mean squared velocity, the average of the square of the velocity, is given by the temperature. So this is easy. So you just have to choose n random numbers from a distribution. So the next question is how to assign positions. And so in order to assign positions, you have to put the particles by hand inside your simulation box. Now, in order to do that, the first thing to decide is that what's the target state point? Is it a crystal or a liquid or a gas? If it's a crystal, then the atoms are will be put in a lattice, in a periodic lattice. Or if it is a liquid or a gas, then they are put randomly. So first you need to look up the phase diagram. So here is an example of a temperature versus density phase diagram of a simple model complex fluid called the Lennard-Jones fluid. So there are various lines. So at the moment, you don't need to know what are those lines. Just see that there is a region of phase space where the system is in a gas phase, in liquid phase, and crystal phase. And there are regions where there can be 2 phases can coexist together. So there is a mixture of 2 phases. So this information is essential to start with, to know what are the state of your phase of this stable phase of your system. Now, Okay, so here I want to say that from time to time, I mean, in this part, so I'm going to mention few challenges. So these challenges are kind of pointers to mention some technical issues, and this will also serve as a pointer to various kind of further directions or further advanced issues which you can explore later as part of your self-study. So the regarding initialization, there is one challenge is that if you take if you want to generate a liquid configuration, so the density, so liquid densities are very high, and in that case, it's difficult to generate a random configuration for technical reasons. And a common trick to overcome this challenge is to place the atoms deliberately in a periodic lattice and run the simulation. Now, if the stable state is a fluid, then the structure will automatically melt. The crystal will automatically melt, and you will get a random configuration just by the application of the molecular dynamics. So basically, in this case, in terms of technical skill, you just need to figure out how to place atoms by hand, either randomly or on a periodic lattice. So here is an example of how to do that. So I will show you kind of a piece of the code or a pseudo code rather. So this is a piece of the code called init, whose purpose is to initialize the ND program. So there are various lines. So most important is to look at this loop. So this I is a particle level, and n part is the number of particle. So this loop runs from um, the from 1 to n, so order of n loop. So its first line is x is the position. So it just shows that, so it calls another function called lattice underscore pose, whose job is to place the particles on a lattice. And the second line is the velocity. So this ranf is a random number generator. So it assigns random velocities to particle I. And the rest of the part of the code is not so essential now. It is just to make sure that the average of the velocities is 0 and the square average is equal to the temperature. Okay, so the next part is to, so now you have a simulation box, so you know your density and temperature. So you choose the volume of your box, and so and you have put n particles inside that box. So now you want to calculate the forces. The interparticle interactions are modeled by various force fields. And so what are these force field, or what are the interactions? Now, this is a difficult question because it depends on the material of choice and the phenomena of choice. And here is this table on the left side is give you examples of different kinds of materials. For example, complex fluids like water or aqueous solution, or molecular liquids or ionic liquids or colloids, liquid crystals, interfaces, polymers of various shapes, crystalline solids, and biomolecules like protein or micelle or membrane or DNA, RNA. So people study a wide range of materials, and obviously you can expect that you need wide range of different interactions for different materials. And similarly, people also want to study various range of phenomena or properties. Like like instead of studying a specific material, you might be interested to test a fundamental theory, or you are interested in phase transition or the critical phenomena, or you want to do some analysis of the structure, like how the structure changes, or
What happened? Got stuck. Shilarita, Dr. Sengupta.
Hello?
Yes,
Am I
you can
audible?
hear. Yes, yes.
Okay, fine. So so I have to share the screen again, is it? Is it?
I think so.
Okay. Is it good now?
Yes.
Okay, great. Yeah, so what I was telling is that so people want to study different kinds of materials and different kinds of properties or phenomena like phase transition or structural properties or dynamical properties like diffusion coefficient, viscosity, etc., or defect formation, uh, propagation of shock wave, radiation damage. So you have a variety of different things that you want to do, and so depending on what you want to do, you have to choose your force field carefully. So for example, the demands are kind of contradictory or maybe complementary, because if you want to study a material, let's say, then you want to reproduce all the properties of the experimentally known properties of the material as accurately as possible. For example, if you are studying water and you know that water has a density anomaly as 4 degrees Celsius, then you want to choose a force field which actually predicts a density anomaly at 4 degrees Celsius. On the other hand, when you are studying interested in some like a like a generic phenomena like phase transition, then you might not you might not be interested in knowing various details of the system, but your goal is to look at the universality, and in that case you want to choose as simple as force field as possible. So because of these reasons, like designing a force field is actually an industry. You can do PhD who's just to uh, design a force field, and these force fields are already there, so one doesn't need to do this by himself. The standard force fields are available. So I'm going to give you an example of a standard force field. So this is one of the simplest one. It just have a two-body interaction, which means if you have two particles, then they will exert force on each other. And here I show you the interaction potential. So basically, this models the van der Waals interaction, which means that if the particles are far away, they will attract each other, and as you which is due to this dipole-dipole interaction. And when they are very close to each other, then they will try to repel each other, which is the Pauli exclusion principle or quantum effects. And then there is a sweet spot in between, some particular optimum position where the potential energy is going to be smallest. So this mathematical form of this function is called the Lennard-Jones interaction, which some of you maybe already know. So the mathematical form is not important. The only thing to realize is important is that it is an isotropic. So it depends only on the distance of the particle, but not the orientation of the particle, which direction they are. All directions are equivalent. So, for example, if you study complex fluids like metallic glass and colloids, then the interactions are often modeled by Lennard-Jones potential. So yesterday I was listening to a talk in which someone was simulating DNA molecule, and even in that case, the various monomers in the DNA have so it's a complicated force field, but one part of the part of the force field was actually modeled by such Lennard-Jones type potential. So now, so the challenge, the technical challenge in doing the simulation is that the force calculation is the slowest part of an MD code. Why? Because if you see there are n particles in the system, and then if you count the number of pairs, possible pairs, you see they are of the order of n square. So the runtime will scale as n square. And obviously that is not, so you will be limited by your choice of n. So if you want to do a larger system size, you want to apply various tricks to speed up the calculation. So I will mention one simple trick which is applicable for short range force like this case. So you see that the force is essentially zero beyond a certain distance. So what you will do is that if you have a particle in your simulation box and then you put a cutoff around this spherical cutoff, and you say that any particle which is inside that cutoff, they will interact with each other, but any particle which is outside that cutoff, then the distance is so large that the force is basically zero. And then you just need to calculate the forces only between pairs within that cutoff. And these pairs are called the particles around the central particle are called neighbors of the central particle. And so you just need to figure out how to how to make a neighbor list and keep track of the neighbor list. And that trick actually helps a lot. It reduces the scale. One can show that the runtime now scale as of the order of n log n instead of n square. So that's a huge speed up. So note that this is possible for short range force, but if you have a Coulomb interaction between electrostatic interaction, which is a long range force, then you cannot apply this trick. And here is an example of the pseudocode. So this piece of the code is called force, and its purpose is to determine the force and the energy. And here I show you these two loops. So you have two particle levels I and j for two because there are pairs, so there are two particle levels, and hence this loop will run for n of the order of n squared times because it's a loop over all pairs. And so this line applies periodic boundary condition. So I mean, from today we are not, it's a technical issue, we are not going into that. So the key line here in this code is this line, which is the definition of the Lennard-Jones interaction. So this is the line that gives you the force, the potential, and this line is the force. And then this line will calculate the energy. Okay. But now I should also mention that in most of the situations, most models the forces are given by the two-body terms, two-body or potential, interaction potential energy is a two-body potential. But there are certain situations where there are three-body forces. What do I mean by that? So this situation comes in the case of various network forming complex liquids like water and silicon. So what is a three-body force? It basically means that you have a triplet of atoms. And once you have a triplet of atoms, then they are coming close together. And then you can sort of say that they form bonds, meaning they are interacting, they are interacting with each other. And the bond has a bond angle, theta. And so this is a type of interaction where changing this bond angle, so there is a certain preferred bond angle, changing the bond angle will cost you energy. And hence there will be a force to change the bond angle. And since you need three particles to define a bond angle, so this is an example of a three-body force, which means that if you just have only two of them, this force does not exist. You need minimum three particles for this force to exist. And this is very common in polymers, for example. Now, if you have a three-body force, then there are, and for n particles, there are of the order of n cube possible triplets. So that means that the calculation of three-body forces are even slower than pair forces. And that's why the people generally try to avoid models with three-body interactions because they are computationally costlier. So one trick is that for some cases, depending on if the mathematical function of the interaction potential allows you, it is possible to represent the three-body forces as sum of two-body terms. And in that case, the code speeds up the code from of the order of n cube to of the order of n square, and then you can apply this trick of the neighbor list to further speed it up to the order of n log n. So one example where this is possible is something called Stillinger-Weber potential, which is a force field designed for silicon. Okay, so the third piece. So now you have state of the system at t equal to 0. You know the position. You have placed the particles inside your simulation box. So at time equal to 0, and you have assigned the position and velocities, and you now also know the forces between the particles. So you know the acceleration. So now you are ready to integrate the system or update the system to know what will be the state of the system at delta t later. So this is the MD integrator engine, and so this integration, so is done numerically, and there are various algorithms available for doing this MD integration. And so I'll show you an example of one of the most earliest and most accurate and still most widely used algorithm, which is the Verlet algorithm. So remember that I mentioned about Luc Verlet, who was one of the pioneer, and this is one of the contribution of him to this field. So the basic strategy is to do a Taylor series expansion and then truncate. So what you do is that, so this is, by the way, is a little bit equation heavy slide, so bear with me kindly. So what we have is on the left, we want to know the position of the particle at the time t plus delta t. And what we know is the position, suppose we know the, and we Taylor expand the position in terms of delta t as a small parameter about the position, known position at time t. And then the first term will be the position at time t, second term will be the first derivative of position, which is the velocity, third term will be the second derivative of position, which is the acceleration, fourth term will be the third derivative of position, and so on. And suppose in this algorithm, in the Verlet algorithm, you truncate the series at the fourth term. So you introduce an error which is of the order of the delta t to the power fourth power of delta t. And you do the same thing with now you switch the sign of delta t. So you take a position which was little delta t times in the past. And since the sign of the delta t is just flipped, so the odd powers of delta t are flipped, even powers remain, the sign remains the same. And then you write down the second line. And then if you add the first and second, then all the odd powers of delta t gets cancelled. And you end up with the equation where so on the right hand side you have the known position at time t and known position at time t minus delta t in the past. So you know the position of the particle at two different instances, present and past, and the force. So, and of course there is a truncation error which is proportional to delta t to the power 4. Hence you know the position in the future using this equation. So this is the Verlet algorithm. Now in this algorithm, you don't actually need the velocity information, but for other purposes, you may want to calculate the velocity. So what you do is that if you now instead of adding these two terms, if you subtract the future from the past, then you get equation for velocity, which is correct up to third power of delta t, and which is written here. So by using this relation, you can calculate the velocity in terms of the position, and you can recognize this to be the central difference formula for calculating the derivative. And here is the example of a piece of the code which does that in actual code, or say that a pseudocode. So you have a piece called integrate, whose job is to, or purpose is to integrate the equations of motion. So now you see you have a particle loop over all particles, which goes from I equal to 1 to n. So the first line is the Verlet algorithm, which is same as this line here. So this xx is the future position. So xi is the present and xm is the past and f is the force. So knowing the present and past and the force, you get the future. And this vi is the velocity, which is exactly same as this formula. So you have the two positions, present and past, from which you get the velocity. And the rest of the code is not so important here. They are just to define, to make sure that the velocities are following the Maxwell-Boltzmann distribution properly and calculating the energy of the system, etc. So this is how you can do the numerically integrate the equation. So now there is a issue here, which is the choice. So you see that there is a parameter which we have not specified, which is the delta t, the time integration. So this is the fundamental, the smallest resolution of time. So this is the integration in this step of integration. So we have not specified this parameter. And so now we should tell a little bit about this parameter. Now, if you choose a large delta t, then you can cover a long time window of simulation. So of course, it is preferable to have a large delta t. But there is nothing like a free lunch in life. If you choose the delta t to be large, then the truncation error of the traveler series will also become large, and then that makes this integration scheme unstable. In the sense, you will see various unphysical effect. For example, even though the system is by design, the energy is constant, if you actually measure the energy, you will see that this is no longer constant. So so it will violate the law of energy conservation, which is unphysical, which is due to the error in choosing a delta t large. So now you may ask that, okay, but suppose so that integration, the wireless scheme was truncated at the second order in delta t. Suppose if I truncate at higher order, if I include higher and higher order correction to make the Taylor series expansion more and more accurate, maybe then I can choose make the delta t higher, larger. Now you can of course do that to some extent, and the price to pay is that now you have to store higher and higher order derivative of position. So you need to store more information, and that requires more memory. So this was a problem in the early days of molecular dynamics simulation, where memory was computer memory was is not imaginable today, few kilobytes or maybe not even megabytes. Nowadays when we talk about memory, we talk about terabytes, gigabytes and terabytes. Those were unthinkable in those days. And even if you talk about the RAM, nowadays even the desktop computers have 16 GB or 32 GB of RAM. So memory is no longer a big issue in the case of this kind of simulation, unless you have a really large system size. But there is another much more fundamental source of error, which prevents, which I should mention here. So this is the fact that at a very fundamental level, the phase space trajectory that the particles are following are actually chaotic. Because if you take any large enough system size which is at more than 3 degrees of freedom, the phase space trajectories will be chaotic in under Newtonian dynamics. Now, what's the consequence of that? The consequence is that it will depend sensitively on the initial condition. What do I mean by that? So let's say that look at this equation, and here the left hand side is the position in future, and let's call this the true position, the actual position of the particle. And the right hand side is a truncated Taylor series. So let's call the truncated Taylor series as the simulated position. And if the Taylor series contained all the infinite number of terms, then it would have been the actual position. So the truncation introduces an error, which is by the integrator, the MD integrator. So we can think of there are two trajectories: a true trajectory, which is the infinite Taylor series, and the simulated trajectory, which is the truncated Taylor series. And there is a small difference at the beginning, at t equal to 0. Now the consequence of the trajectory becoming chaotic is that any such difference, no matter how small, is going to, so the two trajectories are going to be exponentially divergent at later time t. So this is called a phenomenon known as the Lyapunov instability. Now, so usually these things are not covered is not relevant when you write or simply doing a simulation of MD. But if you think of it, if you can sort of right to become skeptic about the whole business of doing a molecular dynamics simulation because of this Lyapunov instability, then how can you become sure that this whole tool works? For example, I can do a trajectory and stop and store the positions and then restart the simulation. Now, by storing the position introduces some error because you can only store in a finite amount of variable space in your computer. That introduces another truncation error. And what I'm telling here is that the truncation errors are going to be exponentially divergent, no matter how small the error is. And it is actually amazing that the whole method of MD actually works despite this issue. There are deep theoretical reasons for that. Some of that is known, and some of that is still not known. So this is beyond the scope of today's talk. So I just refer to the section 4.3 of this book by Frankel and Smith for further discussion. But take-home message is that delta t cannot be too large. So now I come to the most interesting part of this MD simulation, which is to calculate the properties of interest or the observables. So what I showed so far, so these three pieces actually is by them, initialization, force calculation, and MD integration. By them, you can get a standalone MD code. So there's MD simulation as a tool is complete. And it will give you the time evolution trajectories of particles. You can make a video which will show how the particles are moving in space and time. But just having a trajectory is not useful because the real fun is to calculate the various macroscopic observables. So I'm going to give you 3 examples to illustrate different kinds of observables, different types of observables that you can calculate in the simulation. And so the first example is specific heat, which is a thermodynamic quantity. A similar observable is pressure. So here is I show the mathematical formalism, which standard statistical mechanics formalism, by which one can define calculate the specific heat. But let's not go into that in detail. So look at this red box. So specific heat is basically measures the fluctuation. So E is the total energy at a given configuration, and the right hand side gives you the fluctuation in energy from the average value. So specific heat is basically measure of the energy fluctuation. And given a configuration, you can calculate the forces, so you can calculate the potential energy, and you also know the velocities, so you can calculate the kinetic energy and add them up, you get the total energy. So you can calculate the energy fluctuation for a given configuration, and then you do that for many configuration and take average. So that is the basic strategy or rule by which you calculate specific heat and this kind of observables. Now, if you are listening to this talk so far keenly, then you may want to protest and say, wait, there is some cheating involved, because the formalism here assumes that it's an NVT ensemble, because it is temperature is constant, whereas the code that we showed here, this code is what I described to you, uses the NVE ensemble where the energy is constant. So how can you have a fluctuation and in NVT? Is there a contradiction? So, well, you can give two answers. So first you say that, okay, in the thermodynamic limit, the thermodynamic properties are going to be independent of ensemble. So you just go and buy a bigger computer. But in reality, the answer is obvious, that you have to carefully select an appropriate ensemble before you design your simulation. And there are various ensembles, so which are standard. So I gave you what I described to you is how to write a code in NVE. But of course, you can do it for in given other conditions like NVT, where temperature is constant, NPT, pressure and temperature is constant, number of particles constant, stress and temperature ensemble, grand canonical ensemble, etc. So now, how to simulate in different ensembles? So there are two steps. So basically, you need to know the probability of observing one microstate, which comes from the statistical thermodynamics, and you need a simulation method or numerical method to simulate the constraints that keep the pressure and temperature, etc. fixed. So remember, in theory, you just say that the system is in contact with a reservoir, and there's a wall or piston which keeps the pressure constant, or a wall which keeps the energy, which maintains the energy flow and keeps the temperature constant. So you have to simulate that wall or piston in the simulation, in the code, to sort of to make a mechanism to keep the pressure and temperature constant. So you have to basically introduce the reservoir in the simulation. So the take-home message is that real-life application demands MD in different kinds of ensembles, and this is one of the advanced issue which I cannot cover in today's talk. But if you need to be aware about this and this advanced topic. Now I come to the second type of quantity, which is the entropy, or equivalently free energy. So entropy and free energy are defined as a sum over all microstates, which means our strategy that we learned here, that compute the observable for a single configuration and then take average, is not going to work, because what one needs is to take sum over a population of microstates. So you have to define a population of configuration and then integrate over, use all of them to calculate the entropy. So this is a different kind of observable. Now there are various ways to do that, and one of the simple way is the method of thermodynamic integration, which I illustrate using this picture here. So basically, the idea is very simple, is that even though entropy is not calculable for measurable for a single configuration, but you can measure the derivative of entropy which will give you the pressure or energy. So what you do is that you choose a thermodynamic path, like a path is temperature. So this is a temperature density plane, and you define a thermodynamic path in this plane. And along this plane, you calculate a derivative of free energy or entropy and integrate between two state points and that will give you the difference in free energy or entropy. So for example, in this case, if you go from this point to this point and integrate over the energy, then you will get a difference of entropy between the reference, this what is called high temperature reference point to low temperature target point. And now, but this will give you only the difference. So from difference, if you want to go to the absolute value, of course, you need to know the absolute value of entropy at a reference state point. And there are two reference state points. One is the ideal gas, the other is the harmonic oscillator. So this will give you, so you need to start from one of those reference points to get the absolute value. Okay. Now, this third example is a dynamical quantity, and the example is diffusion coefficient. So what you do here is that, so the problem is that you have a tag particle, point particle inside the liquid, and it is doing random walk. So it goes from one place to another place, which means that the mass is diffusing, a point mass is diffusing from one place to another. So the problem is to calculate the diffusion coefficient. Now, how do you? So what do we mean by this? How do you calculate? Is that so? Suppose you consider the density or concentration of the particle given by at a given uh, position x at a time t, which is given by the quantity c. And since this is diffusing, so this concentration is changing with time. And so if this is diffusing, that means there will be a current. So because the mass is changing, so there will be a current which is given by the Jx, and you and this is basically this is proportional to the gradient of the so you can write down the fixed law of diffusion, which is the macroscopic law of diffusion, which is an input. So you say that the concentration is the diffusion is happening following, this is the rule by which it is happening. And then this current, so you can to conserve the mass, the current will be related to the gradient of the concentration, which is the continuity equation. And this defines, this is the diffusion equation, and this defines the diffusion coefficient D. So this is a macroscopic phenomenological rule. And if you just combine these two equations, eliminate the current, then you get the what you call the diffusion equation, which is given entirely in terms of the concentration. Now choose your initial condition. So say that at t equal to 0, the tag particle was at origin. So at t equal to 0, x equal to 0. And this is given by this delta function. Now with this initial condition, it is known that the solution is exact and analytical. There is an analytical solution where the concentration at a later time x and t is given by a Gaussian in x and not so Gaussian in time. So this profile you can also interpret as kind of a probability that tells you what is the probability of this observing this point particle at a time at a position x and time t, given that it was at origin at time 0. Okay, so once you know this distribution, then you can calculate so x is now the displacement, and you can calculate the square of this displacement and the average of that, so which is called the mean square displacement, and then take the derivative of this mean square displacement and use the diffusion equation, and then you can show that the diffusion coefficient is given by the time derivative of the mean square displacement. So this is how Einstein proposed to measure diffusion coefficient of a Brownian particle. And you can now, this is an example I show of calculated mean square displacement for a binary mixture of Lennard-Jones type complex fluid. So all these different curves, all of them are at same fixed density, and different curves present different temperatures. So the temperature is going down. So the lower the curve, that means the temperature is lower. And so the thing to note here is that if you look at the t tending to infinity, the long time limit, all the curves look like a straight line. So they are linear in time. And hence, if you measure the slope of the different curves, that slope will give you the diffusion coefficient from this relation, which is known as the Einstein relation. So, okay, so now I have given you some idea about a basic part of an NB code and what you can calculate, different types of quantities that you can calculate. And based on this, you can now appreciate that the various demands of real-life applications and the limitations of the MD as a tool. So it is when you use a tool, it is important to know, not only know the advantages, but also the limitations of a tool, where you can break the tool and where you can use it. So the first challenge or limitation is the accuracy. And there are two various ways. So what I'm going to say here is to give you the sort of the issue, and then to show you how people try to overcome these issues or challenges. So the first challenge is accuracy, and so the first thing is that this MD integration introduces numerical error. The time steps cannot be too large, which we have seen before. And you cannot do much about this, except there are certain clever tricks which uses variable time steps, but this is a limitation, and you just have to do the brute force longer time calculation. And the other issue about accuracy is that if you are doing material science, and then you want to give a more accurate description of the macroscopic behavior of a material, and there what people try to do is to sort of improve the force fields. So this depends basically on the microscopic force field or the interaction potential, and you just want to design a better force field with more which gives you better match with experimental properties. The second challenge is about the high system size and the time scale. So as we said before, that the slowest part of the MD simulation is the force calculation, because the force calculation scales with some powers of n, and hence the runtime increases with n. So to give you a feeling, so in present time, the typical MD simulations employ from few hundred or few thousand to few million particles. And if you compare with a typical experimental sample, they contain about Avogadro number of particles. So even though some of these the extreme MD simulations employ billion particles, even then you can see that it is nothing compared to Avogadro number. So the system size that you can take in a MD simulation is much limited compared to an experiment. And of course, since the integration time steps, you cannot do much about it. And if you put the numbers, you will see that the time steps comes in the order of picoseconds normally. So even if you have the longest MD simulation with a billion time step, it still covers only 1 millisecond of real time, and which are much less compared to a typical experimental time scales. And these challenges are a big challenge of MD simulation. And so far, the only way to overcome this is to increase the raw computing power, which is the our next point. So you have these hardware level solutions. So what you can do is that if you take a typical desktop today or laptop, so it contains anywhere between 1 to 16 processors normally. Now you can connect those processors, you can increase the number of CPU processors and connect them by connecting them together and scale them up to hundreds of thousands, and they become supercomputers or cluster supercomputers. And then roughly about so the current, and here I show a kind of a pie chart of world's top 500 fastest supercomputers, and the pie chart shows the country-wise distribution of them. And so these top 500, so they in today's modern top 500, they can do of the order of 1 peta floating point operations per second. So they are petascale computers. So that means 10 to the power 15. And so this was achieved in 2008, and all the usual. So if you go to a typical research institute like IITs or TIFR or ISC, Math Science, who has good computers in India, so they are typically teraflop computers, because they are the number of clusters is of the order of 100 to 1000. Number of CPU processors are of the order of 100 to 1000. If you go to US or Japan or China, so they have the monster supercomputers with 10,000 processors or more, which runs on petascale. And the next goal of is to achieve this exascale, which is 1,000 times faster, so of the order of 10 to the power 18 flops. And this is actually achieved this year in March 2020, which was achieved to do actually this coronavirus simulation. And you may wonder that where all this computing power is useful. So I give you an example. This is a recent paper. So one of the place where this kind of exascale computing will enable, so if you read the abstract, exascale computing will enable development of new predictive multi-scale models, transforming how we study the behaviors of organisms and ecosystems. So in the biology, because the complexity is large in biological systems, so there people are kind of hopeful about this or try to use these exascale computers. Now the another direction of hardware level solution is to use a GPU. So GPUs are the graphics card in your computer, which are focused on graphics rendering, for example, computer games. And they are designed, so their goal is to do the real-time update. So their design is different from the CPUs, and the GPUs dedicate more hardware, that is the number of transistors to computation. So they can employ, so each of these computers has small power, but the number of them, instead of 8 or 16, you can have 2,000 or 4,000 or more. So think of it kind of a, let's say you want to push a heavy truck, and you employ 8 bodybuilders to do the pushing, versus you employ, let's say, 2,000 or 4,000 children to do the pushing. So it is this kind of difference between the hardware design. And this has become very popular in last 10 years, the use of GPU. And people have shown that using GPU you can achieve anywhere between factor of 10 to factor of 100 speed up in calculation. And the software level solutions are basically, you need to write codes, or you need to have MD codes which are actually capable of fully utilizing all this available computing power. So there are various paradigm for doing that. For example, this see this so the basic paradigm is to parallelize the code, or writing a parallel code which are using like MPI or OpenMP, etc., and also use the power of GPU, and that requires also change in the code. You need to modify your code so that GPU can understand the code. So these are the software level solutions, which I will tell a little bit more in maybe next few slides. So now, so I'll give you some pointer to the literature. So there are of course hundreds of papers and websites, but just to keep things simple, I point only a few standard textbooks which focuses on understanding and explanation. So there are two standard textbooks. One is by Frankel and Smith, which is shown here, and the other by Allen and Tildesley, shown here. These are kind of the Bible in this field. And this Allen Tildesley book is more, so the Frankel and Smith focuses more on understanding, and Allen Tildesley focuses more on like a cookbook, which gives you methods to do, and it also comes with the functioning example codes available online. I also mentioned two other books which are by Rappaport, which is a good source for a special type of molecular dynamics which involves collisions, like collision-based MD or event-driven MD. And there is another book which is slightly old, but it has excellent in explanation, a very simple explanation, beautiful explanations for different techniques by J.M. Haile. And now of course, I so far maybe I have given you the impression that you have to write your own MD code if you want to do simulation, but that is not true, because there are various, if you want to avoid writing your own code, it is possible. There are various the softwares or packages available online, and I give you a few examples. So these are examples which are kind of packages that I am personally familiar with, and so, but this is not certainly not a comprehensive list. So the first one is this LAMS. So this is the LAMS stands for the Large Scale Atomic or Molecular Massively Parallel Simulator. So this is a very kind of a beast which does many things. It has lots of different interaction potentials or force field defined inside it, which can do solid simulations of solid materials like metals, semiconductors, biomolecules, polymer, various mesoscopic system, coarse-grained models, etc., granular materials. There is also NAMD, which is more optimized or designed for the large biomolecular systems. So the NAMD also comes with a visualizer program which is very useful for making movies and seeing actually visualize the system, which is this VMD or Visual Molecular Dynamics. It's and this is a standalone tool. You can use it without using MD and vice versa. And as I mentioned that there are nowadays people have written code or packages for doing a molecular dynamics simulation, which utilizes the GPU. So for example, this ROMD, which stands for this Roskilde University Molecular Dynamics package, which is optimized for GPU with simulation for up to a few million particles. And I also mentioned a couple of softwares or MD packages which are more popular in chemistry field, like CHARM and AMBER, chemistry and maybe biotechnology field. And this AMBER is not, so out of these examples, so AMBER is commercial, so you have to buy the license. The other ones are open source, so you can freely download and install and use them. And all of these good thing is that if you are a self-learner, then what you need is help from the community, and all of them have extensive documentation, tutorials, how to, and for community-based user forums, active forums.
You have 5 minutes.
Yeah, it's almost time end. Maybe the 1 or 2 slides left. So we have this lot of different communities. So all of them are very active and popular. So okay, in the next 5 minutes, as the organizer has kindly reminded me, so I'm going to present a case study quickly of showing an example from recent research of how the MD simulation can lead to real progress and understanding in basic research and breakthrough. So what I show here is a plot of two time series. So these blue circles are the in potential energy, or the fluctuation of potential energy, and the red squares are the fluctuation in pressure. You can say this is actually virial, but you can consider it to pressure. And what you can see is that they are highly correlated. So this is a system of I think Lennard-Jones potential, Lennard-Jones model. So they are very correlated. So this was so the correlation is very strong, and so this observation was actually discovered by MD simulation. So, and initially this was called a strong pressure energy correlation, and you can actually quantify the strength of the correlation by doing a scatter plot of all these points here, the pressure versus energy, and you can see that they are linear, and the correlation coefficient is point. So the correlation is more than 90%. It's almost 93%. So this is a strong correlation between pressure and energy. So this was the observation, and this was surprising because this was not expected. Because why it just means that pressure and energy are kind of not independent, and why this should be. Now I can show you that this is not true for all. So this is a complex liquid, you can say, and this is not true for any liquid. So it is a counter example. So the same plot of pressure versus energy, the same scatter plot, and it looks like a circle or a black hole, which round shaped, which means that the correlation is very weak, maybe 5% or so. Yeah, 0.5%. So this is a water. So here is a model where there is weak correlation, and here is a model where strong correlation. So this discovery was done by MD simulation, and then people naturally tried to understand why, and etc. So the first thing was that they tried to find that is there any system where this is already known, and they found that yes, there is a system of special liquids called inverse power law models, inverse power law or IPL liquids. In those liquids, the interaction potential goes as R to the power minus n. It's an isotropic potential, and one can show that by calculating the partition function, that you expect the correlation to be perfect. So the pressure and energy are not independent; they are related to each other. They are proportional to each other. So you get a perfect correlation. And as a consequence, you can also show that temperature and density are not independent parameters. So temperature, so the state phase is actually one-dimensional. In phase diagram is one-dimensional. So the partition function does not depend on density and temperature separately, but as a particular combination of rho to the power gamma over t. So gamma is some exponent. So the partition function is a function of rho to the power gamma over by t. Rho is density, t is temperature. And so this is called the density temperature scaling of IPL liquids. But here, this system is not IPL potential. It's a very different potential. And so then the question was why this particular system obeys this kind of approximate density, almost perfect density temperature scaling. And people have found many examples of this kind of liquid, where you don't expect the scaling to hold, but you observe them to hold. And then there are, over a last almost a decade or so, many people have studied this phenomena. I have also wrote a paper on this. Uh, so they have found various properties of that. So there are detailed analysis of forces and structures, etc. And there are now a good understanding of the underlying phenomena. And there is a concept of isomorphism, so which is beyond the scope of today's talk. But the point is that I will just mention a couple of consequences which came fairly recently, like this year, is that there's a consequence of this kind of a hidden scaling invariance in the liquids. You expect that so if you measure the dynamical quantity and thermodynamical quantity, then you expect that there will be some kind of a quasi-universal scaling, which is shown here. So on the y-axis, I plot the diffusion coefficient, which is measured in units of density and temperature, and on x-axis we have the entropy. And you see that for a wide range of different systems, they have a master curve. So there is a kind of a, but not all of them, a lot of them, but not all of them. So you have a quasi-universal scaling of the between the dynamics, the diffusion coefficient and entropy. And similarly, you can have the between two different transport coefficient. You have with the diffusion coefficient and viscosity, you also observe a kind of a master plot for wide variety of systems, and which is this is an example from literature which is done entirely by molecular dynamics simulation using very extensive calculation of very high performance MD simulation. So this will just give you a kind of a flavor that molecular dynamics is how it can be used in doing cutting edge research in today. With that, I stop, and thank you for your attention.
Okay, so thank you, Professor Shilarita Sengupta, for a very, very engrossing and inspiring talk, and also very informative and on a very exciting topic. So the session is now open for questions. If the participants have any questions.
Participants, if you have any questions and if you want to know any information related to the topic, please post it in the question answer section or in the chat box. So this session is now for question answer. So kindly post your question or drop your question in the question answer box or in the chat box.
I have one question, which is that, so we discussed, you discussed this molecular dynamics simulation in this talk. So as a tool for simulating many particle classical systems. Right? So how would you compare this method of simulation to a Monte Carlo method of simulation, which is also for classical systems, for statistical method?
Well, they are kind of complementary tools. So if you calculate kind of thermodynamic quantities, then you can use either of them. And for example, energy or specific heat or entropy, you can use either of them, and you expect that the final answer does not depend on whether you have used Monte Carlo or MD. They will match as long as you are in equilibrium. The difference comes when because in the dynamics, in the sense that molecular dynamics gives you how the something is changing with time. and in Monte Carlo there is no concept of time, so you cannot do a time evolution. Of course, you can use the Monte Carlo steps as a proxy of time, but that is not a real time. So so the answer is that if you want to analyze structure or thermodynamics, there you can use either of them. If you are interested in dynamics, then there is no real dynamics in MC. But there are tools or codes which use a hybrid method, which is a combination of MD and MC. So they are very works closely together.
Okay, so you have one question. There is one question in the question answer Q&A. Anirban.
I cannot see the question answer. So, okay, now I can see. So, Anirban said,
yeah, by Anirban. Can you see the question?
Yeah, can we study liquid solid or liquid gas particle interaction by using MD simulation? Well, I don't know what do you mean by particle interaction. If you are interested in studying the, for example, phase behavior or phase transition, you can certainly study using MD simulation. So if you elaborate on what is meant by particle interaction, I can maybe give you a better answer.
Okay. So, if there are no more questions, then let us thank again Professor Shilarita Sengupta from IIT Roorkee for a very interesting and engrossing talk. And we hope to have him again in our midst at some later occasion.
Thank you,
With that,
the organizers,
we
for
end this
giving the
session.
opportunity.
We end this session today, and Mr. Prem Kumar will share the feedback link, etc.
Only thing I want to thank the speaker, Shilarita Sengupta, Dr. Shilarita Sengupta, for giving such a nice talk. Particularly reading of the talk was very nice because he explained everything very slowly, and so that all the participants can understand, even though who are beginner, they can also understand and grasp the extract from your speech. So many thanks to Dr. Sengupta for coming over here and giving your speech and sparing your valuable time with us. Thank you on behalf of our organizer, from the university, and on behalf of me. Thank you very much, and hope you will share your knowledge with us in future also.
Yeah, thank you, Professor Gaur, for your nice and quick feedback. I hope it will improve future presentations.
No, you have done it very nicely, because for particularly those who are you have mentioned initially that particularly those who are postdoc, for them it is very accordingly you have presenting this in lecture, and obviously I think it is good. The way by which you have given the lecture was very good, very nice, nicely presented. Nicely presented.
Thank you.
Okay, so we